But what this presentation is about, it's not so many pages, but I think it's one of the most important presentations for the beginning because it contains the theoretical background, not only for MOSH, but also for the LTGC hyphenation. So the technique we are using for MOSH. Also why we are using it and why we cannot do it in another way. So I think when you have understand these basic principles, it's the very best way to start in the whole MOSH topic, not only application-wise, but also when you have customer questions, etc. Because many things can be broken down to the theory behind MOSH and the theory behind LCGC. Okay. But let's start first about MOSH. I think all of you know it by now. It's for mineral oil contamination, and the MO in the word is for mineral oil. As you also know, of course, there are many sources for mineral oil in our daily life. When we just talk about food in the beginning, there are, of course, you know that when we are packaging food, when we are transporting food, when we are producing food, there are a lot of sources, possible contaminations, and possible ways how mineral oil can get into contact with the food. Here are only a few examples about packaging, recycled cardboard. That was what I was talking yesterday during the lunchtime, that at least in Germany or in Europe, I don't know if it's the same here in Singapore, the first observation of MOSH was in 2009, 2010 in Germany, when it came to pasta and rice in recycled cardboard. Because at least in Europe, you are taking old cardboards, old newspapers, etc. You are recycling it, and at least during that time, noodles were just dryly packed into the cardboard. So you had direct contact between the cardboard and the noodles, and although noodles are not wet, you have so-called gas phase migration, which means over the time, MOSH from the cardboard, from the used newspaper was migrating on top of the pasta, and of course then also found in the pasta. So that was the very beginning where most of the samples were analyzed for in 2009, 2010. Of course, also jute sacks for transport of cocoa is a very big topic, was a very big topic, will be a very big topic in the next 100 years, I think, because when you are spinning the material, you need to use oil to have the material spinnable. And for that, typically mineral oil was used. So when you are spinning jute sacks, you need something so that it has a nice texture, and that was initially mineral oil. They now switched to edible oils, but as jute sacks can be used for many, many times, over 20 years without any problems, you still have jute sacks in around the world which are still contaminated by MOSH. Lubricating oil, food wax coatings. So sometimes you have, when you go to the supermarket, when you have apples, so that they look shiny, that on the top can be just mineral oil to have a nice looking apple. Release surface anti-dust agents, so that's for processing of food, and many, many, many more. So it's incountable how many possible contamination you have. But I think the most important thing is to understand that it's not only one source. You have really over the whole lifetime of a foodstuff, from the beginning to the end, numerous ways of interaction and possible contamination ways. That's also important to understand for the customers when they ask you, I'm seeing now much more in my chromatogram, where it is coming from. That's a question that typically cannot just answered by only one answer. It is, in the end, you need to see the whole picture to understand, and also maybe to analyze at different stages in a food production to get an insight where MOSH is coming from for this specific product. Can be totally different for the next one, but that's at least something customers need to understand. I don't know if this is if this already came into your mind or on your customers, but at least in Germany, when we talk about contract labs, their customers often just want to know where it is coming from. Not only it's 10 milligram per kilogram, but as they need to mitigate, they need to find where the source is. This is the long-term issue and the long-term investigation sometimes. When we talk about MOSH, we also need to talk about, at least in Germany, MOSH got some importance because of the NGOs, so the non-governmental organizations. I would say when we would not have companies like Food Watch or something like that, it wouldn't be such a big topic, and probably we won't have legislation starting from next year. This is only a small number of samples that were analyzed over time by NGOs. So you can see that's essentially, I don't think that is very representative for this area, but at least for Germany, it's more or less the whole span of food stuff. So starting from Nutella down to chocolates and butter and oils and fats, of course, and convenience food. And I think in the last 15 years, there is not many food that was not analyzed for MOSH. So many contact labs just do all type of MOSH. So it's not only edible oils. Of course, what's more important here, because you are in vicinity of all the oil production sites, but contract labs typically just need to analyze everything, not only edible oils or edible fats. When we talk about exposures, I just started with food, but what should not be forgotten is also consumer goods. I think that's not a big topic yet here, but as you can imagine, it's not only food that we are ingesting, but it's also something like cosmetics. When we talk about lipsticks or sunscreen or all that kind of stuff, especially lipsticks, toothpaste, and all that can be orally applied, is of course the same as food. Of course, you are not eating lipsticks, I hope, but it would have the same influence. And also that became a big topic, at least in Germany in 2015, when the first wave of MOSH in food was gone. It was looked what can be found in cosmetics, because a lot of cosmetics during that time was based on mineral oil. So you can imagine when you have lipsticks, for instance, the base material is just microcrystalline wax. It's not that anymore today. It's all based on edible oils and fats. But as you can imagine, when you take a lipstick based on 100% MOSH, it's very likely that you will have also eaten some of that. So it's not surprising that you have that also then in your body. So these are the two big groups of sources when we talk about exposure to the human body. What's important to understand is when we talk about mineral oil contamination, we are not talking about the black goose coming out of the earth. That's probably not something you are seeing in daily life, but we are talking about highly refined petroleum. So I just picked it down here, a typical refining of petroleum. And it's not that important, but to understand what happens, there are many, many steps. So you're starting from typical atmospheric distillation. So you're taking your black goose, you're doing distillation to get the first fractions out of that, like petroleum, naphtha, kerosene, etc., etc. And then you have a very, very high boiling goose where you want to get everything out that can be typically used. So you are switching from atmospheric distillation to vacuum distillation. Of course, petroleum contains a lot of PAHs and toxic compounds. And these are typically removed during the refining of mineral oil. So that's the first thing to understand. When people nowadays talk about MOAH or the potential toxicity of MOAH, when we really talk about highly refined mineral oil, which could be some that is used in medicinal ways, then there are no MOAH inside that are toxic, because they are removed in the first step. So what you're seeing here, extraction of 3 to 7 rings, that's something that is already done in the refining process. What you're getting there are so-called distillate aromatic extracts, so also so-called extender oils. This is something that was used as plasticizers, for instance, in the production of car tires, for instance. It's not allowed today, at least not in Europe anymore, but those type of aromatic extracts could be used as plasticizers during tire production. But the very important step is that one here. So IP346, that's a norm. That's a DMSO extraction of your product, and a gravimetrical test if there is more than 2% of weight inside. In the old days, so in the 1970s, when this test was not present, every product was tested on mice. So on the mouse, you're taking scratches on the back of the mouse, you're applying your product, and you are coming back after 90 days if the mouse got cancer. Yeah. So you can imagine that was a problem when we talk about animal life and all that kind of stuff. So there were a lot of experiments in that time, and this DMSO extraction has very high correlation to this mice painting skin tests. So nowadays it's just a DMSO test, which of course is not giving you a direct answer if this product can cause cancer, but at least that was the idea behind it. And then when we talk about mineral oil, it's typically only the stuff which is in this red circle here. So on the one side, it's food grade wax and micro waxes or paraffins. And on the other side, it's technical white oil or pharmaceutical white oil. Now the question is, why do we still talk about MOAH inside that? Of course, this is by principle, first of all, let's say 80–90% of MOSH. So since it's mineral oil, it's basically saturated hydrocarbons. This DMSO test here and also the extraction is not extracting the 1 and 2 ring aromatic systems. So there is, of course, aromatic compounds inside, but they are considered today, even though they are not, it's not yet scientifically profound tested because it's not enough data there, but these compounds are considered to be non-toxic. So the basic part of MOAH we are talking about is not the toxic 3 to 7 rings, so the PAHs, so to say, but the 1 and 2 rings that are still present after the refining steps. So that's only important to understand for you. If you ask me for my personal opinion, the MOAH topic is nice. We can earn a lot of money with that, but when it comes to the real concern for the human life, it doesn't seem to be a big issue. But this is only my personal opinion. Okay. Since this extraction is never 100% perfect, you will always have a certain degree of 3 to 7 rings inside, but at a microgram level. So at a level that might be comparable to PAHs. And therefore, we have all this stuff coming up now with GCGC, GCTOF, and all the complex stuff we will talk about later. But this is, first of all, the refining process of mineral oil. And when we talk about contamination in food, it's not the crude product, it is highly refined products which are used in lubricating oils, in cosmetics, and all that kind of stuff, which by themselves are, of course, much, much safer than crude petroleum. Okay? When we talk about the structures of the compound, so that's only for the one, for the chemistries, for the chemists beyond us, we have 2 classes. That's why we talk about MOSH and MOAH. The SH is for saturated hydrocarbons and the AH for aromatic hydrocarbons. So 2 classes that by principle need to be separated because they are structurally very different and also from their toxicity, at least from the basic idea, very different. When we talk about saturated hydrocarbons, of course, we have alkanes, naphtanes, so circles, but totally saturated. So no double bonds inside, no aromatic benzene moieties, nothing like that. So can be complex structures, but still no double bonds, nothing like that. Aromatic hydrocarbons, on the other end, by definition, have at least one benzene ring inside. And the separation, or let's say the distinction, is in the number of the aromatic rings. So as I said, the smaller rings, like the ones here on the top, where we have only one benzene ring, we can of course have saturated rings as well, and side chains are by principle much less toxic than when we talk about triaromatics or polycyclic aromatics. That's exactly the same idea which is behind PAHs. It's exactly the same. Where people do not talk much about is that the MOAH fraction also contains so-called heterocycles, so thiophenes and furanes. They are at much lower concentration, and they are in your MOAH humped somehow hidden, but nobody is talking about them specifically. And it's interesting, just checked literature on that quite some while ago. There's also not much scientific literature about toxicity of heterocyclic PAHs. So PASH or PAOH would be the correct term for them. So nobody knows if they are toxic or not. They're inside, but at least up till now, nobody's talking about that. What I already hinted a little bit about is that nowadays it's known that the saturated hydrocarbons are accumulating in the human body. So that's by far the biggest contamination in humans. So when you are 80 years old, 85 years old, and you are dying, you have multiple grams of saturated hydrocarbons in all of your body. That's just accumulating over your lifetime. So in your liver, in the kidneys, and all that kind of stuff. So it's not preventable, but at least scientific opinion nowadays was not the same 10 years ago, or not even 5 years ago. It stated it's accumulating, but it's not causing inflammation. It's not causing cancer. It's doing nothing. It's only for your personal belongings. I just already stated here that because of something I will show you later, it's only saturated hydrocarbons in the range of around C21 to C35. So that's the amount of carbons inside that compounds are accumulating in the human body. Smaller ones are just metabolized. So the human body is capable of metabolizing also alkanes. They can be transformed in fatty acids and also other type of stuff. And when the compound gets too big or too long, the compound or the molecule is just too big to penetrate the human cells. So they are just somewhere and they are just leaving your body otherwise. So that's the basic idea why when scientific tests were done on dead people, that they only found MOSH in this specific carbon range. Of course, when we talk about aromatic hydrocarbons, there's not a simple relationship between the carbon number and toxicity. That's the same as it is also for PAHs. As you know, some PAHs, even though they have the same carbon number, can be highly carcinogenic, while another isomer is completely unharmful. That's exactly the same here for aromatic hydrocarbons. Let's talk a little bit about legislation or regulation. These slides are not yet 100% up to date. I included the final legislation later on. But I just wanted to show you when it got critical in Europe when we talk about regulation. Because prior to 2022, there was no regulation when it comes to the numbers or the levels in. There was no regulative way to withdraw any sample from the market. That was only by by goodwill of the suppliers. Of course, by the pressure of the NGOs, when we talk about Nestle or something like that, when you have an NGO talking that Nutella is containing a lot of MOAH, of course, it's not nice publicity, so they by themselves withdraw products from the market. But since 2022, there was a statement from the European Commission that when a product contains more MOAH than these levels, like 0.5, 1, and 2 milligram per kilogram, in dependency of the fat content, that was always linked to the fat content of a product, state authorities were able to withdraw products from the market. And this is also important to know that's still the base for the legislation that will be starting January 1st next year. It's basically still based on this simple statement. The last toxicological statement was from 2023, and it was stating that MOSH was out of concern. And when we talk about MOAH, that we need to distinguish between the small MOAH and the bigger MOAH. Since scientific data is so scarce and so little, they just could say that in the end, they need to do more scientific research. So up to now, we still don't know if 1 and 2 ring systems, if you ask me, they are not toxic, but I'm pretty sure a lot of universities will study that, and you have a lot of PhDs coming from that, and a lot of people paid for that, with the final result that they are not toxic. For the 3 ring and up to 7 ring system, it is known that there are potential candidates that are carcinogenic. Nobody knows at which levels they are inside food because they cannot be analyzed, because as you might know, MOAH analytics is not the most easiest one. So when you can imagine you have MOAH and you still need to split it in the toxic ones and the not toxic ones, it gets even more complex. That's the basic idea behind GC times GC. But what they stated in 2023 was, under the assumption that when we talk about foodstuff and we have a content of MOAH inside, when the MOAH content, and let's keep on fat and oil, so the maximum level is 2 milligram per kilogram, when only 1% of that would be carcinogenic compounds, then we would have a possible health concern for high consumers and infants, basically, because it's just so little inside. But when it's 10%, it could be potentially a health concern for all people. Does that make sense? Okay. But since this is not known, it's still topic to upcoming research.
Michael,
yeah.
Question, sorry.
Of course.
May I know the difference between EU Commission and EFSA in Europe? How they divide
the EFSA, so the European Food Safety Agency,
okay,
is just a scientific organization. So they are not allowed to give any legislation. So they are doing all the scientific stuff, and the EU Commission is the party which is responsible for legislation. So EFSA did all the scientific research, scientific data, looked into it, gave their statement, and based on that, the European Commission defined the final law.
Okay.
Yeah, so all
thresholds and levels is coming from EU Commission.
In the end, yes.
Okay.
So when it comes to the real laws, it's all coming from the European Commission. And European law is always higher than national law in the European countries. So that means when you have a European law, it needs to be implemented also in all state countries. So, which just means when we come to next year, and this is the regulation for starting for next year, it means that all these numbers need to be implemented in all European countries. I think it's a little bit small, but that's now just marked a few examples. So this is edible oils and fats I just marked. This was just easy edible oils like rapeseed, sunflower, soybean, linseed, and butter. So with 2 milligram per kilogram. I think in this list should be also somewhere stuff like fish oil, which has some higher numbers, and something like olive pomace oil, which has quite high numbers, and I think coconut is also somewhere in there.
Sorry. Coconut, sorry, is above that's below the red square.
Yeah, exactly.
I just want to ask, because like for Thailand, you have your rice bran oil, it's not included.
It's
so
not
like others category.
No, it's not by the name, but you have products derived from and fed, blah 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 blah, and you have unfortunately something like other oils. Here, oils other than those listed in these categories.
Mm-hmm. So I've got another question, because looking at the registration, I understand EU like to categorize rice into cereals.
Yes.
So in this kind of scenario, rice bran oil, will you put under cereal?
No. It depends. In the end, it is only based on the fat content. And since rice bran oil is 100% oil,
yes,
it's not cereals.
Oh, whereas coconut oil, they are going to put it at a higher regulation in 2027.
Yeah, it's because first of all, you have all these intermediate numbers. These were introduced by all the different lobbies.
Yes.
So when you do not have a number, for instance, for rice bran oil, it means there's a very small lobby for that. Okay. But when we stage with coconut, this is because that's something I explained yesterday during the lunchtime. Coconut is when you are starting from the coconut, the first step you are doing is drying of the copra, and this is done on open fire. The open fire, unfortunately, is not only open fire. You are, depending on the farmers, you are also burning stuff like old car tires, stuff you have just on the farm. This fume and all that kind of stuff introduces PAHs. So in crude coconut oil, and you're seeing there's no distinction there between crude coconut and refined coconut oil. So it is just like coconut oil, which means also crude coconut oil contains a lot of PAHs. And when you are analyzing that, you get quite high MOAH numbers, because PAHs, since it's the same chemical structure, is analyzed in some also with MOAH. It is not mineral oil based. That's absolutely clear. But it's very hard to distinguish between those two classes, because chemically spoken, they are 98% the same. Just as a fun fact, we will see slides about this later, not today, I think in 2.5 weeks. It's not always possible to separate, even by GC times GC, these two classes, because chemically it's almost the same. And when something is the same, you cannot chromatographically separate it. I think that's quite clear to all of us here. It's not so clear when we talk about legislation. Yeah, I think they do not understand this specific issue. But in fact, I had communication to a few coconut oil refineries, and their lobby was a little bit late on the numbers. So there will not be any changes anymore to that. They still wanted to increase the numbers, because when you look on olive pomace oil, it's with 10 milligram per kilogram even higher than coconut.
Yes.
Because of the lobby. And yeah, so you have these intermediate levels, which are basically vanishing in 2030. Yeah. So unfortunately, that's the law, and we need to live with that, at least for the next year. I suppose when there are enough people that are claiming, okay, it's scientifically nonsense, or there is problems with that, or whatever, the numbers can be changed in an updated version, but I think for now, these are the numbers we need to live with. And when we just stay on the example coconut, it's all based on the problem that the copra is dried on fire. When you would dry it on sunlight, problem gone. Yeah, so it was basically the same also for palm fat. In the beginning, we had very high numbers on palm fat. Nowadays, I would say all palm fat which is used in the industry is below 2 milligram per kilogram MOAH, even since 2 years maybe. That's all because the plantation and all the farmers just looked at all the vehicles, all lubrication cycles, and all that kind of stuff that can be fixed easily. I know that's for palm oil much easier because you have big plantations. For coconut, because you have a decentralized organization, many small farmers that are working by themselves. And it's much harder, of course, to implement good working practices for 100 farmers. That is easy to understand, I think. But from the scientific point of view, all these contamination could be prevented. And that's the basic idea behind all the law, because the EU regulation or EU Commission is thinking, it is clearly a problem of humanity. It can be prevented. So that's the basic idea why you now have nowadays, for a few products, quite strict numbers. Okay?
Just a clarification. Previous slide, can I go to the previous slide? The 1% and 10% scenario is more for 50% fat and oil and above.
That's not important. It's dependent on the milligram per kilogram found in specific products. So when we talk about oils and fats, it's 2 milligram. But when we talk about rice, for instance, it would be 0.5 milligram per kilogram because of the low fat content of the rice. And then 1 and 10% is always accounted to this number. So 1% of 0.5 or 10% of 0.5.
Oh, okay.
And here it would be 10% of 2 milligram or 1% of 2 milligram.
Understand.
So it's always based on the LOQ for the specific fat content in percentage. That was the basic idea for this scientific statement. These numbers, these scenarios here are based on PAH assumption, because for PAHs there's a lot of scientific data, and EFSA just took numbers for PAHs and tried to use them for MOAH evaluation. It's not 100% correct, but as I said, the statement or this, I think that was a lot of pages, just ended with the conclusion we need to do more research.
Thank you.
Now coming to a few more matrices. It's not only fats and oils that are regulated, but also other stuff like cereals here. So products with, in this case, less than 4% fat. Also stuff like milk. Doesn't make any sense. But interestingly, even in milk you can find MOSH and MOAH. It's quite interesting why you can find it. Interestingly, cows are often, when you take the cow, the farmers are using mineral oil products based, so like cosmetics, so to say. Yeah, so they are using that to rub the cow with cosmetic products. And of course, in the end, you will find that also in the milk. It's not much, and it's basically for beauty reasons for the cow. Don't know why this is necessary, but this is one reason why you find sometimes quite high numbers for MOSH MOAH in milk. Of course, also when you have contaminated food and feed. So when you have feed contaminated with a high content of MOSH MOAH, this is fed to the cow. There's a high chance that you find stuff of that also in the milk. Even though it's digested by the cow, there's still stuff that can be found in the milk. Okay.
Just a quick question. Since we are talking about milk, and milk is a very common ingredient used in cosmetic products as well. Do you see translating into consumer products to monitor MOSH MOAH?
From consumer products, yeah, but of course not at this small. Yeah, so that since this regulation is only for food, the numbers for if there will be a regulation, I don't really think that there will be one, because I think it took now 27 more than 20 years to get a regulation for food. For cosmetics, since when you look on what was already implemented for mineral oil milk-based cosmetic products that they switch to edible oils. I don't think that there will be a regulation, and when there will be one, I suppose it will be much higher values than for food, especially when it's only applicant to the skin. Of course, digest or what is it? Is it migration? Not really. So turning absorption of MOAH through the skin, of course, it's much less compared to oral application. And I think milk products should basically only be on skin products. I'm not aware that you have a lot of milk-based products that you could orally inhale or whatever.
Yes.
The next category that is interesting is spices and herbs, which by themselves doesn't make much sense to talk about fat content because spices and fats do not have fat content. But there is a general limit of 5 milligram per kilogram for all spices and herbs. We will learn later that this is sometimes not possible to achieve analytically because of the nature of the spices and herbs, because they have very high terpenic content inside. This makes it very hard to analyze them for MOAH because these compounds are very similar in structure to MOAH. And finally, I will just talk a little bit more about spices in a minute. But when we talk about composed and processed food, this will only start in 2030. So for everything which is processed food, so composed of several stuff like, I don't know, soups, and I think also instant noodles will be in the same category. This needs to be taken care about only in 2030. And the idea is basically, again, based on the fat content, which means when you have a composed food, first of all, you need to get the fat content of the food. So you need to analyze that. So you need to extract the fat. You need to weigh it. You need to get the content so that you know which category would be the correct one.
Since there are EU regulations for all the different classes, things of food to be analyzed, is the sample extraction step being standardized already? Is there an official method?
Unfortunately not. When we talk about official methods, we only have official methods. Now it's in fact two. So there is an official method for infant formula, which is already, I think, 5 years old, and one for edible oils and fats. But even with the restriction that only vegetable oils and fats. So it's funny that we have a regulation, but no official methods. When we talk about animal oils, even there you have categories like fish oil, where you do not have an official method for fish oil. That's also a little bit problematic. Despite the compound food, coming back to spices and herbs, what also needs to be taken into account is that you have so-called concentration factors, which means when you are concentrating a product, like that's quite common when we talk about spices and herbs. In industry, you do not use marjoram or whatever and put it into a soup. You are firstly creating a marjoram extract, either by, I think it's steam distillation or it's not distillation. It's no, it is steam distillation. Then you have a concentrate of that. You know how much you used for that concentrate. So typically a concentration factor is between factor 10 and 40. And this factor is applied to the LOQ, which means when you are using marjoram, you concentrate it on a factor of 40. Your limit of quantitation would not be 5 milligrams anymore, but 5 times 40. Okay, so when marjoram concentrate is then analyzed, your LOQ is not any longer 5, but in this case 200. Yeah.
It's a new question is meaning powder milk. Powder milk It's a fresh milk.
Or fresh milk. So milk, is it fresh milk?
No, all. So yeah, this in this specific category here, this is fresh milk. Yeah, true. I'm not sure if milk powder by itself is claimed there, because that is also interesting. First of all, of course, also infant formula with all kind of stuff is put in here, and also food supplements, food additives are not yet regulated. But of course, these documents cannot state all matrices available on the market. Everything which is not stated in there is
The last one.
is still using this statement here. Yeah, so this statement is still used for all matrices that are not specifically in this EU regulation. So in fact, still the limits of quantitation based on the fat content. Okay.
Sorry, Marco, I got another question to ask. This is really just for personal knowledge. Milk. I remember milk has very high fat content. What are they setting at 0.5?
Very high fat.
It depends on what type of milk you are buying in the supermarket. So in Germany, milk in the supermarket basically has a maximum fat content of 3.8%. That's basically the milk you are buying in Germany. Of course, when you're buying fresh milk, so directly from the cow, it's then again based on the fat content. So it's then not 0.5 milligram per kilogram. Yeah.
But if the regulation put this, won't be the.
Yeah, honestly, what I can look later on is here index 2. I think there will be stated that it's again based on the fat content. So in the end, if you are not sure, it is always based on the fat content. Yeah, but I'm pretty sure this statement there is based for milk you're buying in European supermarkets. Okay, concentration factors, processed food, and also everything which is not stated in there is based on the old statement. So that will be the way to go in 2027. Okay. It's not so surprising, so to say. So with the scope puff statement before, there's not much change. Yeah, of course, there are a few temporary limits higher than 2 milligram per kilogram when we talk about edible oils and fats, but in general, it's not surprising what we are seeing here. Okay. What I already marked here is just two numbers, because they come important a little bit later. All the MOSH-MOAH analytics or all legislations, all based of MOSH-MOAH in the range of C10 to C50, which basically just means it's an abbreviation for the boiling points. So C10 and C50 obviously have a defined boiling point, and it's easier to talk about C10 and C50 than talking about 174 degrees Celsius and 575 degrees Celsius. But this is the range or the boiling point range where all this legislation is taken for. Even when you have in your chromatograms a lot of MOSH-MOAH higher than 575 degrees boiling point, it's not considered. Yeah, so the end is at C50, 575 degrees. Believe me, when you take normal products, there will be a lot of MOSH-MOAH higher than C50 at the very end of the chromatogram, sometimes even in the next chromatogram, because it's still on the column. Okay? But it's important to understand, because that question comes quite often. What's about the MOSH-MOAH, which is in the chromatogram at the very, very end? It's not considered. It's basically what I already stated before, that compounds bigger than C50, or even C40 was it in the beginning, are not capable to penetrate the human body. Even if you can imagine a C50 PAH, even when it would have 7 rings, needs to have a lot of side chains to get 50 carbon atoms. And when you can imagine you have a big pH, with a lot of alkyl side chains, even that compound for the outside looks like a saturated hydrocarbon because you have a lot of alkylated side chains. And this is the basic idea why also PAH become non-toxic when they have long side chains, because for everything in the human body, also DNA and something like that, it looks like a saturated hydrocarbon. Another regulation we have specifically only in France, it was the very, very first one, is only for mineral oil-based ink. I don't know if this is a topic here for your customers, but every ink that is imported or is to be sold in France needs to be checked specifically for these numbers. It's only for ink. It's for, I have no idea why they put legislation. So it's really a national legislation for ink. Yeah, so we are now already in this statement here, which means every ink that has either more than 0.1%, or when you are able to analyze only 3 to 7 ring pHs or MOAHs with only 1 ppm, so 1 milligram per kilogram, and also MOSH must not be more than 0.1%, is not allowed to be sold anymore in France and also not to be imported. When we now talk about the last sentence, mineral oil saturated hydrocarbons lower than or must not exceed 0.1%. This basically just bans all mineral oil inks. So ink needs to be based on vegetable oil. So this is basically the most important statement in this legislation. So France only allows vegetable oil based or whatever you are using as a carrier material, but it's basically all vegetable oil based for ink. And so mineral oil ink is not allowed anymore. Yeah, and when we are taking vegetable oil, so it's basically then a color, an ink based on vegetable oils. You need to analyze the MOAH content of a vegetable oil. It must be lower than 0.1%, which is easy. Yeah, so 0.1% is 1000 ppm. So 1000 milligram per kilogram. And we have food stuff where we need to analyze down to 2 milligram per kilogram. So 1000 milligram per kilogram is very, very often not a very big problem for vegetable oil-based ink. But this is a very specific one, or a very specific legislation. In fact, we had a little bit of interest from Japan, I think, because they seem to be exporting ink to Europe. Not sure about this, but also all printer ink and all this kind of stuff, all needs to be vegetable oil based. Okay. I just left this slide here in, but it basically becomes non-effective starting from 2027. There are already 2 countries in the European Union that implemented more or less the same regulation as will be coming active for all countries. That's Spain and the Netherlands. So Spain and the Netherlands at the moment are the only countries in Europe that are banning everything that is exceeding the limits we have already talking about. Will be the same for all countries starting from 2027, but only for completeness right now. So today it's only Spain and the Netherlands. Okay. So now we have already talked a lot about legislation. Now let's start with the funny part. So how is it analyzed? Okay. The idea behind LCGC and the MOAH analytics is all based on the problem that a mineral oil by itself is composed of many, many thousand compounds. It's not only single compound, and because it is many, many thousand compounds, as you can imagine, it's not a just think about any other detector despite an FID. when it comes to calibration of the detector, it's always important that you know what you are analyzing. So it's very hard to find detectors in the chromatographic world that just give you a unity response. There is not much there. On the GC world, it's basically the FID. And just looking on these nice humps here, so these are the chromatograms we are getting for the ones who never have seen a MOSH-MOAH chromatogram. MOSH-MOAH chromatograms are not single peaks. As I said, it's many thousand compounds, and since they cannot be separated anymore, it's forming a hump. We call it a hump or UCM, unresolved complex matter. These humps, as I said, are just the composition of our many thousand compounds. And the two, when we just talk about, first of all, this very nice big hump in white paraffin oil. These humps typically, when we take a mineral oil and when we are injecting it or when we are analyzing it, the shape of the hump, I would say in 80% of the cases, is giving you a very nice Gaussian shape. So always looking like that. I already talked about that, but do you know why it looks like that? It was, I think, on the 5th slide, maybe today, this morning, when I talked about how mineral oil is produced. What's the first step in doing mineral oil production? Distillation. Removing of aromatics is the third step. But distillation is basically the same thing we are doing in gas chromatography on a non-polar column. Yeah, so we are using completely non-polar columns, so 100% PDMS. And effectively, that's the same you would do in simulated distillation. So as you might know, the chromatograms in simulated distillation look very comparable to those. And they look like that because when you are producing mineral oil, you are already doing distillation. So distillation is normally done in a way that you are setting a distillation temperature, and then you are just getting everything at this specific temperature. Of course, that's not a 100% threshold. There's always left and right around this temperature distillation, which of course is then getting lower and lower. This is exactly what you are seeing here. So for these mineral oils you are seeing here, distillation temperature was set to exactly these carbon numbers. And what you're getting here, this typical Gaussian shape, is just a typical observation for distillation. That's not a 100% threshold. Yeah, so the hump shape looks it looks like that because it's a result of the distillation process of the mineral oil. Does it make sense? Okay. Since when we just would inject a mineral oil into an GCFID, we would just get one chromatogram, one hump.
Not symmetry. Like this. So it should not come from mineral oil.
Not so easy to answer.
Or maybe have two thoughts of the mineral oil is that
Is it like because of the shape? Is it because we got two-thirds of the mineral oils, or is it like
again, please again?
Is it two-thirds? That means they are asking if it's not a very nice hump. It's not to have a discount. Two humps. Is it mixture of?
Could be. So what you often see, we just have now our chromatograms, so retention time and signals. What you often see is chromatograms like we just start with the solvent peak.
Super.
And chromatograms might look like that, so that they are maybe looking like this. So that is not, you would normally expect that it should look like this. Yeah, so when we just talk about this example, that it might look like that. Of course, when you are analyzing food stuff, you are not analyzing pure mineral oil. You have already refined food or refined edible oil. And one important step in oil refining is also deodorization. During deodorization, you are doing effectively again a vacuum distillation. So you are heating up the oil under vacuum, removing all volatile compounds, which means what you are not seeing is the part removed during the refining of the oil. Because typically refining of oil removes all hydrocarbons until C24. Therefore, the hump starts from a symmetrical shape into a non-symmetrical one because you have cut all the stuff before C24. And again, since distillation is not a perfect process, it looks like a non-symmetrical hump. So not like a sharp cut in the chromatogram, but you are still having these smaller shapes compared to the larger backside. That's very often the case. The other way, what you are also observing, we'll see this also later, is when the contamination is coming from migration, so gas phase migration, then it typically looks like that, a big hump in the beginning, but a very steep decrease after that, because migration is limited by the temperature. So you will have a bigger side on the left because that was migrating at the possible temperature. Then you have a steep decrease because temperature was not high enough for that, for the migration. When you now think about that a food can be composed of many contaminations, you can have infinite combinations of that stuff. Yeah. Therefore, very often you do not have symmetrical humps in your chromatograms. Okay.
Is it a common way to infer if I see maybe multiple hump, it might be multiple source of process contamination?
Yes, what you typically do, and this is also done by the contract labs, for instance, when they want to analyze where the contamination is coming from, you very often get chromatograms that, for instance, look like that.
Oh,
yeah.
This is very common.
This is very, very common because, in fact, this only means these are two contaminations. So this is just the addition. When you just would add two chromatograms, then it would look like that. It's just two contaminations. Yeah, two sources, exactly. Yeah, as I have shown on the second slide, I think, since you have a lot of steps during the production of a foodstuff, every step potentially can add its own contamination. So even 3 humps or 4 humps is a possibility. Yeah, of course, when it comes to quantitation, it's not important because the regulation is all based on the total MOSH-MOAH contamination. So it's just, you need to integrate from the beginning C10 to C50. You're taking the total number, that's it. So from the regulation, it's absolutely not important if it is 1 contamination or 10. It's the total number which limits if this foodstuff can be sold or not. But when it comes to the interest of the customers, it's very interesting for them to understand, okay, these are 2 contaminations. So it means most likely that I have 2 steps in the processing of the food that are leaking somehow mineral oil into my food.
I'm wondering why the straight chain alkanes sit on top of the hump, not mix within the hump.
Yeah, that's quite honestly the real chemical answer for that. I cannot give you. That's just observation that obviously everybody is doing. That isoalkanes and naphthenic alkanes are within the hump, while N-alkanes are sitting on top. If you are interested, I need to look into the literature. Maybe I can answer it tomorrow morning. But at the moment, I just can say from pure observation that they are sitting on top when they are small enough. As soon as they are overloading the GC column, which would then be one reason why you need to do aluminum oxide cleanup, they start to sit also in the hump. this is the reason why we need to do aluminum oxide cleanup, because they look like a hump, but they are basically only N-alkanes. So when we would only inject mineral oil in a GCFID, we would get only one chromatogram and only one hump. As you can see, the humps in this examples for MOSH and MOAH have exactly the same shape, which is not 100% always the case, but at least what's always the case is that their maximum is at the same detention time, because basically, since it's the same contamination in the beginning, so it's coming from the same distillation process, they are separated on silica in two classes, and each of this class is injected separately into a GCFID. Therefore, it's one important rule of thumb that the MOAH hump basically needs to resemble somehow the shape and the maximum detention time of the MOSH hump. That's also important when you are when you're interpreting chromatograms. It doesn't make any sense that you have a MOAH contamination in the front and the MOSH contamination in the back. That's absolutely not possible when we talk about mineral oil. Of course, when there would be a synthetic aromatic hydrocarbon inside your product, which honestly is very unlikely, you can have it everywhere in the chromatogram. But when we talk about mineral oils, because it's coming from the same source and only separated on the liquid phase into two classes, they still need to have somehow a link in the two GC chromatograms. So that's more or less the most important rule of thumb when it comes to interpretation of chromatograms. If it makes sense what you are seeing there. Because that was what we slightly talked about yesterday. Since MOSH is out of concern when it comes to regulation, you could think about why I'm analyzing MOSH. That's basically only because of the root source analytics. So the MOSH chromatogram sometimes is easier to interpret than the MOAH chromatogram. When it comes to source analysis for the customers, it's good to have both chromatograms, because you are not making the instrument cheaper when you are not analyzing MOSH. You are not getting faster when you are not analyzing MOSH. It's basically you could discuss if you would save the money for the aluminum oxide cleanup. I will talk about that later, but basically the instrument setup is still the same. So we are not saving anything by not analyzing MOSH. We are not getting faster by not analyzing MOSH. So having this additional information is very valuable when it comes to interpretation of the data. What we typically see, depending on the refining degree of a mineral oil is, as you can see, the MOAH chromatogram in these three examples look very, very different. From, let's say, 50-50 down to almost 0. This is just a result of the refining process. The more you are refining on a mineral oil, the more you are removing the aromatic hydrocarbons. For instance, these can be removed when you do hydrogenation. Yeah, when you just put hydrogen gas under high pressure on ready nickel catalysts into the mineral oil, you are just destroying, or you are just saturating them. So you are producing more saturated hydrocarbons. But this is basically how it's done to get from a mineral oil looking like that down to that. So this one here would be white paraffin oil, which is typically used on medicine. And this is still crude, so quite high MOAH content. But when we talk about lubricating oil, you are somewhere between, because you are also changing stuff like viscosity and all that kind of stuff when you do hydrogenation, for instance. So this is sometimes not done till the end, but stopped in the middle. Okay. So that's the idea. I hope that's clear why we are using a GCFID, because we just don't have standards for 10,000 compounds. And we need somehow a liquid-based chromatography based on silica, because silica is cheap and it is very easy to separate saturated and aromatic hydrocarbons. Okay.
Since the retention of both MOSH and MOAH is so important, so for both lines, the alignment needs to be good, right? If it is not aligned, it could be a problem from our system.
It can be, exactly. And this is what we will talk about later. Having this indication is very important when it comes to interpretation of the chromatograms. When you have, since we are using two distinct GC channels that are not linked to each other, in worst case, when you have two GC columns that are very, very different, and I had one where you had, let's say, 2 or 3 minute detention time difference between the two channels, it's not possible to link that anymore. So therefore, this is one of the practical part later. We will also talk about why we are changing the flow rates on the columns to have, again, linked chromatograms. That's not for quantitation. That's only for the interpretation.
So if customers analyze this manually, like only using a single panels, and they still link.
Yeah, because it's the same column. Since it's the same column, you do not need to think about this. Yeah. That was what I already talked about, but just only to summarize it here. GC separation does not allow to separate MOSH and MOAH, so therefore we need liquid-based. And the separation is basically only based on boiling points. So that's why the chromatograms look like they are looking. Now the question, when we talk about food, how do we get MOSH and MOAH out of that and how it is analyzed? That's just a nice picture I used during my PhD, I think 10 years ago. But when we talk about food, obviously it can be very complex. You have a lot of bioproducts like edible oils, triglycerides, essential oils, sugars, pigments, all kind of stuff. So we need to somehow extract MOSH and MOAH from it. That's basically, there are many, many ideas for that. Yeah, one idea is just liquid extraction. So very simple methods. Try just to use different liquids. Try to extract that. More elaborated methods use saponification or hydrolysis. But before we come to that, I just want to show you how much more analytics is done manually, so that you are valuing why we are doing LCGC. Yeah, so basically, MOSH-MOAH separation is based on column chromatography. So bare silica, as you would do it in university or in the lab. So with the steps involved, like packing the glass column manually, since we need to use glass, because plastics, unfortunately, has also products in it that are contaminating our chromatograms. So you will need to use glass columns. You need to condition it, sample loading, separation process. You need to use a rotary evaporator to remove the solvent. You need to resolubilize it. And then, because we're analyzing up to C50, it's typically done by a cold and column injection. Because whoever of you try to analyze quantitatively with an SSL or MMI or PTV up to C50 is seeing that the chromatograms, when you look on alkanes, basically will look like that. You are getting nice alkanes in the beginning, and then they are getting smaller and smaller because temperature or transfer of the sample from the liner onto the column doesn't work anymore. That's basically what you are seeing there. And I know up to C50, up to C40 is easy, but when you get higher than this, can be very problematic. Therefore, column injection is the method of choice on that. So injecting the sample on the column, when it's on the column, it is on the column. Yeah, so there's no way for the sample not to reach the detector when it's not absorbed on the column in between. Okay.
So it is conventional approach, right? Because it involves the top end. That means the lower boiling point will be lost because you so
in fact, what you're doing there in this method is you're putting a keeper solvent into your into that. So typically, when you are working this way, before you are removing the solvent, you are typically putting a little bit of toluene inside. Because when you are then gently evaporating, you are not losing C10.
So normally up to which carbon number? I'm just curious about the condition.
So traditionally, you mean including solvent evaporation?
Yeah, so
I would say up to C10.
C10. Anything below is lost.
Yes. Yes. So in fact, this is the way people started to work at MOAH in 2008, 2007. Yeah, so you can still download the method from the German BFR, that's the German Risk Assessment Center. And honestly, if you only have 1 or 2 samples a day, it's perfectly fine. You can work this way. Of course, it gets a little bit troublesome when you are doing a lot of samples at the same time. Okay, so this is exactly the same idea, but when you're doing more than 30 samples a day, it can be a little bit challenging in the lab.
Yeah,
okay.
I think silver nitrate. Yeah, I think silver nitrate.
Yeah, in the manual method, you need to use silver nitrate because the silica particles are not 5 micron, but bigger. And when they are bigger, they do not have the same retention capability. So you need to put in it 0.5% silver nitrate to get the same retention. So that's the idea of the necessity. I didn't put that inside because it would be too complex at that stage. But yeah, when you're doing the manual method, you need to have 0.5% silver nitrate in the silica tab. When you would use smaller particles, unfortunately, the sample is not flowing anymore through the column. Yeah. So that was already in the 1980s. The main idea why LCGC hyphenation was invented, because basically it's just a combination of automated sample preparation. So in fact, the HPLC is just for us a miniaturization of the column chromatography we are doing. We are not doing fancy HPLC, UHPLC stuff here. So no 1000 bar pressures or whatever, but it's basically just a smaller version of our column chromatography. Yeah, the idea is here, LC is giving much easier the capability to separate classes, like MOSH and MOAH in this case. It's easy. Yeah, you do not need to invent anything. While GC has the advantage of the capillary columns, so high separation power, and of course, basically for MOSH MOAH, it's the FID we want to use. It is, of course, much easier to evaporate normal phase solvents. So organic solvent, evaporation of organic solvent is much easier, much faster than we would think about reverse phase evaporation. There are a few applications that are also working on water methanol based. So basically high content methanol, only a little bit of water, because water unfortunately always has a problem when it's getting hot because it creates steam. The steam is stripping our separation column, and that's basically a bad combination. But the good thing here is the class separation of MOSH and MOAH is easily done in hexane dichloromethane, so easy solvents with low boiling points, and typically a 2 mm HPLC column is fine for the flow rate and the fraction volumes we are creating. You can imagine when we are taking bigger columns, because of diffusion inside the column and all that kind of stuff, we get bigger fractions. We also have higher flow rates. When we're taking smaller columns, we get smaller fractions, but we also have less capacity in the column. So 2 mm columns is a nice spot between 1 millimeter and 4.6 millimeters. So that's basically the idea why everybody is using 2 millimeter column. Because we are getting volumes in the range of 200 to 500 microliters. For MOAH, it's in the range of 500 microliters. So now the question is, how do we get 500 microliters of MOSH and 500 microliters of MOAH into the GC without the loss of C10 to C50? That's now the basic idea we need to think about. That's a picture of an optics injector. So basically, when I started with the whole project in 2010, the first idea we had, because Axel Sembrau is also a dealer for the GL Science optic injector. So the basic idea was we are using the optic injector for that. Since it might be an idea, what the first idea here was, we're taking our HPLC column, we are connecting it to a syringe that can be closed and opened, and we are injecting it into the optic, and we are evaporating. That's then the so-called speed controlled injection. So we have a controlled speed. We are dripping into the liner, we are evaporating, we are getting a chromatogram. Unfortunately, this is a speed controlled evaporation is always based on so-called concurrent evaporation, which means the solvent evaporates at the same speed as it is introduced. Otherwise, you would flood the liner. Concurrent evaporation always loses the volatiles. So this type of injection works only when you want to analyze starting from C18, because C18 is the first, more or less the first hydrocarbon with a boiling point that high that it's not evaporated. On the other hand, when you are injecting smaller volumes, like only 100 microliter, when the liner is big enough for that, you can just do a so-called rapid at-once injection. So you are injecting everything into the liner. The liner is big enough for 100 microliter. The idea is doing, because you're injecting very fast, doing the evaporation of the solvent, the liner is cooling down by more than 40 degrees. So you are creating a cold spot in the liner, and then you can also retain volatiles. But this works only for volumes smaller than the liner. Yeah, so basically it works fine for 100 microliter, not so fine for 500 microliters. So basically we needed to switch to another transfer technique, and therefore the so-called large volume and column transfer was used. As I said, conventional injection is using our volatiles. What we are doing here instead is we have a transfer valve which can just guide the eluent of our HPLC column into a T connector, or in this case it's a Y connector, not important, and we are mixing it with the carrier gas in here, and we are shooting it. So that's a mixture of gas and liquid. We are shooting it in our pre-column. Inside the GC, it looks like this: 10 meter pre-column, uncoated capillary it is, then another T piece, and a so-called vapor solvent vapor exit. I will show you in the next slide what especially happens in the stages. Then we have our separation column connected to that, and then an MS or FID, whatever. Yeah, so only for the setup of the instrument. Yeah. At this stage, I think it's easy to understand. Okay. Now, let's try to understand what is really happening inside the columns, because that helps you also in service to understand why you are seeing certain chromatograms, why a chromatogram looks strange, why peaks are looking fancy, and all that kind of stuff. When you have understood this principle, everything else becomes much, much easier. Okay? So what happens first is this solvent vapor exit valve has two positions. The first one is open, so just an open exit. And the second position is basically closed. For now, just consider it closed. In reality, there is a capillary with a very small waste gas flow. So, but it's basically just closing for now. When we are transferring, we are switching this valve to open, which means we have still a GC instrument, which means the carrier gas is coming from the top. What happens? This is a 0.53 millimeter column. This is a column with typically 0.25. What happens when we open here a valve to atmospheric compared to closing when it comes to the flow rate on the separation column?
You lost everyone.
Okay. So, first of all, closed. We are considering, or we are getting our carrier gas from the top. So the carrier gas is flowing through our columns. It's closing here, so it cannot exit. And it is just reaching the detector. Okay? When we now open the solvent vapor exit, what is the consequence for the carrier gas? When it comes to the amount that reaches the detector, it's much less, because effectively we have just a 10-meter column anymore, which is directly connected to the atmosphere. Because of the high restriction of the separation column, basically only a very small purge gas flow is still flowing on the column, which means when we are injecting or when we are evaporating, our separation column is basically protected from the solvent because there's not much flow anymore on it. So everything which is entering here will be exiting here. Only a very small amount will be transferred onto our separation column, which is also nice because otherwise you need to burn a lot of solvent in the FID. Okay. So what we are doing here in the first stages, as I said, we have our HPLC valve open. We are mixing in the T piece, the liquid and the carrier gas. So what you are seeing here basically in the blue color is our liquid flooding our column here because injection speed is higher than evaporation speed. Okay, therefore, when we would just leave the instrument transfer all the time, this flooded zone, this is called the flooded zone, becomes longer and longer and longer and longer. And then someday it will be exiting completely liquid out of the SVE. Okay? Does it make sense to this point? The open temperature is below the boiling point of the solvent, which means we are getting a liquid inside the column. So it's not evaporating 100%. It is evaporating a little bit or quite a bit because we have carrier gas, which will dissolve quite a bit of our liquid even below the boiling point. That is exactly the same principle you would apply when you are doing in the lab nitrogen purge on liquid. So even at 20 degrees, you can evaporate hexane, which has a boiling point of 70 degrees, just by putting nitrogen on top of it. That's exactly the same idea here. So we have basically for this application 60 degrees, which is below the boiling point of hexane. We have carrier gas coming from the backside or mixed into the T piece. We have a liquid layer inside our pre-column, and we have quite a bit of the liquid evaporating already by the fresh carrier gas. So we have a combination here of liquid on the walls of our column. We have inside the liquid, we have all of our compounds trapped because the liquid has much higher retention for the compounds compared to the gas phase. So the idea why we are not losing anything is just we have liquid there. Okay. As we have injected faster than we have evaporated, means, as I have explained, the flooded zone gets longer and longer. At some stage, the transfer is finished because our 2 minutes or 1.5 minutes are over. So we are closing the transfer from the HPLC side. We have still open our solvent vapor exit, and we have an amount of liquid inside the column. The column is still long enough that there is still open space there. So as you can see, we have now flooded about, I don't know, 60%, 70% of our column, but we still have unflooded area here. What now happens is still the same that we have seen in the slide before. We are not injecting anymore, but our carrier gas is still flowing from the backside. So what now happens is our flooded zone will be vanishing from the backside. Yeah, so we have fresh carrier gas from the beginning. It will evaporate our liquid. It will flow through this area, and this flooded zone gets smaller and smaller from the backside. So in the end, that it is mainly only in this area here. Okay, so that's what we are seeing here. We have our flooded zone compressed to this area here. When we are evaporating all of the high boiling compounds like C40, C50, as they are not going into the gas phase, especially not at only 60 degrees, they are just left on the spot where they are. Yeah, so what you are seeing here in green are all the high boilers distributed somewhere in the area of the flooded zone. So we have now more or less on the separation. We have done more or less a separation on the first column here. We have our high boilers spread here in this part, and we have now our compressed flooded zone in this area here. We still do not lose the volatile compounds because the volatiles will just dissolve again and again as long as there is still liquid here. Yeah, so they will, of course, evaporate when we are evaporating the liquid phase in the beginning. These yellow dots, of course, will also evaporate because they are volatiles, but they will redissolve again in the liquid before that, because retention in the liquid is much higher than it is in the gas phase. So the idea for that, this is called solvent trapping, is we are using solvent to trap all of our volatile compounds. We have now closed our solvent vapor exit, so everything in this state would stay in this state. Or now all the carrier gas is now pushed again back onto the separation column. So we are pushing everything on our separation column now. And because we have now a higher pressure in the system, our band is a little bit compressed and now pushed on the separation column. And what we are doing for the volatiles is a typical GC separation band. Yeah, so we have a band in the pre-column, and this is now starting to separate into our volatile compounds like C10, 11, 13, 14, 15, 16, as soon as we are increasing our oven temperature. The high boilers are still on the spots where we left them. So they are still spread here. As we're saying, it's about 70%, means in worst case, a compound like C50 has a bandwidth or a peak width. That's exactly what we need to define here. A width of 7 meters. Do you know how broad a compound at the beginning of a typical GC column can be at maximum when you want to have a nice peak in the chromatogram? Do you know the numbers? Or have any idea? Maybe I can paint that.
Something the separate.
It should be like a multiple choice.
Now we are not doing multiple choice. But let's say that's our separation column, FID. And we are injecting our sample. Or let's say it is only C50 in our sample. How broad can the C50 band, the initial band, that's the correct term, how long is it allowed to be in the beginning of the column to have a nice chromatogram with C50 in it?
How long?
Sorry. We can call it length, of course, because as you know, chromatography is making compounds always broader, not smaller. So when you already start with a very broad initial band length, of course it gets even longer at the end of the column. And typically on a typical GC column, this length must not be longer than 20 centimeters. Yeah, so when you're injecting into a typical GC column, you can start with about 20 centimeters. It gets broader in the end. So in the end, I don't know, you will maybe have 25 centimeters, but this is giving you a nice peak. We have now an initial band of 7 meters. Yeah, so 700 centimeters. Yeah. So we need to find a way to get that back to a compressed peak. Okay. And why this works is because this first column, which I just called a pre-column, another name for that is a retention gap. And the name is because it's a gap for retention, which means this column has much less retention compared to our separation column, which also means when we are increasing the oven temperature, the compounds here will move much earlier at a temperature much lower than they would move on the separation column. Therefore, they are moving quite fast as soon as we are reaching an appropriate temperature, and they will accumulate at the top of our separation column because of the stationary phase. We have no stationary phase here, and we have a typical stationary phase here. So that is what's called the retention gap technique. It's not because it's a fancy name. It is a theoretical background here. Okay.
I would like to ask, right? Using this, we are injecting 500 microliter of HPLC salt.
Yeah.
Right? So your retention gap, when you design this, right? What's the volume?
That's not that important because we are
to prevent overflow or that you need to
exactly
have enough space.
Exactly, you need to have enough space. So this is typically a 10-meter column. The volume of the column is only I need to calculate, but it would not hold 500 microliters by themselves. So what we are doing here is called partially concurrent solvent evaporation, which means we are injecting faster than we are evaporating, but the column does not hold or does not need to hold the complete volume. It only needs to hold the amount of volume that's not evaporated in this stage. Yeah, so we are not injecting everything at once. We have two parallel processes, injecting and evaporation. And typically evaporation rates are in the range of 70 to 80%, which means we are only accumulating about 20% of the liquid.
20%, 100 microliter.
In the end, yes. In the end, yes, which means, interestingly, MOAH would also work on a 5-meter column. That could be done, but 10 meter is easier to get.
I see. As we evolve immediately evaporate those solvent vapor,
Yeah.
but not the liquid. The liquid is still retained in
The liquid is retained in the retention gap. What is exiting here is only the vapor. But of course, when you look at the exit of the solvent vapor, there is liquid again, because it is just decondensing again. But at this stage here, up to here, it is gas. It is not liquid.
The liquid is not
No.
it's not the
No.
liquid used to retain
Exactly.
the boiler.
Exactly.
Because I went and calculate the 500 microliter volume, right?
Now, true. This column is not big enough to hold all the volume by itself. It is only big enough to hold the proportion which is not evaporated.
Okay, now it makes sense.
Yeah. So in fact, with a 10-meter column, you could do injections up to, I think, 1.2 milliliters with the same technique. Then it is again too small. Then you would need a 20-meter or 15-meter retention gap.
Just a question.
Mhm.
I do not know if very states is Chinese secret or not. Because you guys can assure that the recovery of C50 is more than 80%.
Yeah.
But why are you guys so confident that you can make sure the retention gap is?
Or do you run the best sample
Or is it something
That's
unique?
because that in fact is because do you ever asked yourself why you are getting certificates for the retention gaps?
Yes.
Yeah, that's why I'm testing all retention gaps,
Okay.
or at least all batches of the retention gaps. So all retention gaps we are selling, I'm testing 4 of them before we are selling them.
That's the
Yeah.
question. Because I think some of them you see customers look at why do we need to purchase from Treasury? Just say, of course, you get recovery.
Yeah.
But what is the science behind the recovery? How do we say that they are different from others?
The problem is, as you might know, we started the system with retention gaps from another company. So that was also Restec as the separation column. But in 2017, Restec got problems in the production of the retention gaps. The surfaces inside the retention gaps were not deactivated enough anymore. And this process only works when you have a perfectly deactivated retention gap. And then we needed to find another supplier. And since then, we are selling our own branded retention gaps.
So you guys did a QC check before setting up.
Yeah.
Should deactivate.
So, if it's not the epidemic, there's a chance to.
Yeah. In fact, what we are seeing, or what we have seen in 2017 was, let's say, up to 50% loss of C50. So absorption of C50 in the retention gap. No chemist at Restec could answer me why it is lost, but it was the case. Yeah, we do not believe how long I needed to discuss with them until they believed that they are losing an alkane, because alkanes are the most deactivated compound. Typically, you are not losing alkanes, but it was the case, unfortunately. And it's also very difficult. It was very difficult for them to check it, because this observation is only done in a large volume injection. So when they injected just one microliter, it had a nice chromatograms. But when you're injecting 500 microliters, they are losing C50. And this is basically because of this retention gap technique. Because when you're injecting only 1 microliter, this 1 microliter is not really influenced by the retention gap. It will just shoot through the 10 meters without any big interaction. But since the high boilers are having longer contact with the metal surface without any solvent, because in this stage, what we are seeing here, it's just high boilers, metal surface, nothing else. So That's completely different compared to a 1 microliter splitless injection or cold uncolumned injection.
So in that case, those we did in the injection
Yeah.
forms, you will
Yeah.
come out at the next injections.
Unfortunately not, I never found them again.
It's just
Yeah, finally in the column. They're part of the column.
Okay. So we are furtherly increasing our oven temperature, and of course we are then separating also our high boilers. So that's easy. And in the end, we are getting a nice chromatogram that looks like that. But in the end, these are completely two different processes. So from C10 to maybe C17, more or less, we have the solvent trapping is responsible for recovery of our analytes, and everything here is recovered by the retention gap technique. Which also, we'll see this later in the troubleshooting, you can have chromatograms looking bad at the beginning of the chromatogram, but nice in the end. Or you can have chromatograms where the end doesn't look nice, but the beginning looks okay. Yeah. So either way, this is because of the two natures of retention we are using. Solvent trapping versus retention gap technique. So when the first part of the chromatogram doesn't look nice, it's because there were a problem with the solvent trapping. When the backside doesn't look nice, it's a problem of the retention gap technique. That, for instance, was what we have observed with the Vestec retention gaps. The chromatograms looked nice in the beginning, and they looked like that in the end.
this can give us a clue.
Yeah.
The front is
Yeah.
the analytical column,
Yeah.
the back is the retention.
Yeah.
So if the what you said happen like this decrease, should we change the retention gap?
At the first stage, yes. We will learn that later. Not sure if we learn that today, but typically you are injecting a standard for this chromatogram. And it is very complicated to get that standard first into solution, because C50 is an hydrocarbon that is not soluble anymore in hexane. So the standard is coming in cyclohexane, but C50 at room temperature is solid in this solvent. So you need to heat up the standard to get everything into solution. And you do not believe how many customers, and also service units in the beginning we had, where the chromatograms looked like that, but it was not due to the columns, but it was due to the standard. Yeah.
You give up the standard, but it's sitting on the tray or
How long will solidify again?
In the end, it's a thing of concentration. So you do not inject the stock solution, but when you are diluting it to the final concentration you need for the injection, you can just keep it on the tray. It's only a problem of the stock solution. We have done a lot of tests. So typically you are doing at least a 1 to 100 dilution for that. And in this dilution, C50 remains in the liquid. It will not solidify as long as you do not put the vials into the fridge. Because we have done that in the beginning. And I remembering a service technician that used that standard and was looking, I think, 2 days for columns. In the end, it was only the standard.
How many columns?
The diluted.
Yeah, the problem is the retention time standard doesn't need to go into the fridge. So it can be put into it, but of course you need to keep in mind that you need to warm up it properly. And I will later show you also in the slides how to prepare it in a safe way that it works all the time. It's not the only way, but it's a way where I can guarantee that it works all the time. Okay. So this is now a typical alkane chromatogram we are getting from a standard. And one of the requirements of the analytics is that all the marked peaks here, so C10, C20, C50, that they are all having a recovery higher than 80%. At least when we are talking about the ISO norm for food. When we talk about the infant formula method, it's even 85%. It's not only 80, in this case, it is even 85%. Yeah, so this is basically not a problem for C10, it's basically a problem for C50. Because when the retention gaps get old, or when they start to have deposits of the matrix of the samples, the retention gap technique doesn't work anymore. Because when you have matrix inside, the matrix behaves like stationary phase. When you have stationary phase in a retention gap, it's not a retention gap anymore. So you will observe peak splitting, peak tailing, and all kind of crazy stuff for this area of the chromatogram, all related to too high retention in our retention gap. So let's go one step further and have a look into the into the HPLC chromatogram, because that's quite easy and we need at least to have seen it once. As I said, we are using 2 millimeter columns, and in the beginning of MOSH and MOAH, the idea was that we want to inject samples like edible oils, etc., directly after dilution. That was the basic idea in the beginning. That was until nobody was thinking about 2 milligram per kilogram LOQs. They were more thinking about 10 milligram LOQs, and therefore the design of the HPLC column, etc., was done to assure injection of about 20 milligram of triglycerides, which is sufficient to get LOQs to 10 milligram per kilogram. That's only to explain why the column has the size it has. Separation is based on N-hexane dichloromethane, so that's a gradient. What you're seeing here in blue is just the gradient we are using. We're starting with 100% hexane, and then it's a very fast gradient up to 35% dichloromethane, which will then separate MOSH and MOAH. We have a UV detector set at 230 nanometers. The UV detector by itself is not needed for the quantitation, only for diagnostic cases. The 230 nanometers have the advantage that when you look on the height of the signals, the UV cutoff of dichloromethane is higher than 230 nanometers. So for the ones not aware of HPLC, a UV cutoff is the lowest wavelength at which a UV detector is not showing the absorbency of the solvent. So typically when you are quantifying with a UV detector, you need to set wavelength higher than the UV cutoff. Otherwise, you are getting crazy baselines because they are showing you also the gradient of the solvent, which is typically not needed when you are doing quantitation on it. But here, since we are using it only for diagnostic purposes, we are below the UV cutoff. So what you're seeing here, 35% dichloromethane, 100% dichloromethane. That's what we are seeing in the height of the signal. What we are also seeing is, when you look on the slope of the gradient, you would typically expect that you are seeing the same slope also in the wavelength or in the signal, because the gradient should be observable in the signal of the UV as long as we are below our UV cutoff. So that would be the case when you would do, for instance, reverse phase chromatography. Then you get the same slope also in the UV signal. What we're seeing here is only a steep increase. That's because we are not doing reversed phase or not partitioning chromatography. Normal phase chromatography on bare silica is so-called adsorption chromatography. Adsorption means it is all of our compounds are absorbing on our silica particles. This is not only true for the analytes, it's also true for the solvents. And dichloromethane is adsorbing on the particles, and only when the particles are completely full of dichloromethane, they will exit the column. That is not the same for the burst phase partitioning chromatography. Therefore, on adsorption chromatography, you get always, independent of the slope of your gradient, you will always get a steep increase in the signal. That phenomenon is called solvent demixing. Only if you're interested. Yeah.
It's a lot of GC.
Yeah, it is for GC. You typically do not think about this stuff. Okay. By this gradient, we are getting a proper separation between the two classes. Since saturated hydrocarbons do not have any retention on, it is always eluted in the void volume of the column. That's always the case. So saturated hydrocarbons start to elute with the void volume of, with the void time of the column. Therefore, MOSH is always, or in many cases, looking perfectly, even when the separation did not work on the HPLC column. Because as you can imagine, when the gradient didn't work, or when the pump has any problems, or when somebody put wrong solvents into the bottles, the MOAH separation can be influenced because it needs some kind of polar modifier to be eluted. While MOSH, regardless if you're using hexane, pure dichloromethane, pure other solvent, it will always be eluted in the void time of the column. Okay. MOAH itself, this is now an injection of an internal standard. In the UV signal, you cannot see so much. What you always can see is a nicely separated pyridine peak. This is one of the compounds from the internal standard, and some non-resolved peaks in combination with the increase of the baseline. These are the other 4 compounds of the internal standard. They have UV activity, but as we are mainly doing column chromatography, we are not separating these compounds. So they are just eluting as some kind of a hum or something like that. Okay? As soon as both, yeah, sorry.
Can be like
Not always. Not always. What you always can see is the steep increase, but you sometimes, when it's very dirty and you have problems that it was not cleaned up properly, you have a co-elution of other compounds at the same time as pyridine. So, yeah. It's since UV detection is based on the Lambert-Beer principle. You have only co-elution, which means the UV signals will be just adding up. So you don't have something like quenching, because in fluorescence detection you would have quenching. In UV detection it is always a summation or a sum of the signals. But this can be the case, yes, when you have compounds from the sample, or you have highly contaminated samples with a lot of MOAH inside, you will see also the MOAH signals here. They can co-elute also with the pyridine. That is possible, yes. After the separation of MOSH and MOAH, we are reversing the flow rate of the column for a backflush, because after every separation, there is a backflush of the silica column with 100% dichloromethane. That's always the case from, I think, 6 minutes up to 15 minutes. So the idea is when we have matrix compounds, it's very likely that they are still on the top of the column. So it's easier to reverse the flow rate to remove them and not to try to force them all the way through the column. After the 15 minutes, the flow is again reversed and we are re-equilibrating to the same conditions as the beginning. So from the HPLC side, it's a very simple separation. It is not even possible to be more simple than this. Okay.
Well, guys, this simple.
If anything is parameter, so we need contaminate in column.
Mhm.
How long we can use the 100% dipropagate?
If you want to,
use
not a problem. If you want to, no. If you want to try to reactivate the column, you can flush it all the time. So for 10 hours, not a problem. Unfortunately, dichloromethane has a very low elution strength in normal phase. So when you have very highly polar compounds, you can flush for 10 hours, but you cannot remove those compounds. So typically, what you are doing in this case is take the column out of the instrument, connect it, in best case, to another pump, where you have something like methanol, ethanol, isopropanol, because these solvents are much more polar, and you are removing compounds from it. You will see with a very long used column over, let's say, 1,000 to 2,000 injections, you will see when you are connecting isopropanol to it, you will suddenly get out colored stuff from it. So colored substances all absorb on the column because dichloromethane is not strong enough to elute these compounds.
Common approach when we use the color studies of 10% methanol ECN. Is it okay to do that?
You mean when you want to flush that externally? You could do, but it's typically it is better when you go to 100% alcohol, because then you have the highest elution strength. Yeah, so typically 100% alcohol, then going back to dichloromethane or hexane. Because one problem when you are flushing the columns is with something like isopropanol is that the silica tries to hold the isopropanol. So you need a lot of time to remove all isopropanol again from the column. But externally, easily possible.
So your recommendation to regenerate it is just pure IPA.
Yeah.
Pure
Pure IPA, pure DCM, and then against pure hexane.
and how long for
Regenerate.
With isopropanol, or in the end with hexane.
Which one?
Isopropanol is not the biggest thing. So I would say half an hour at a flow of, unfortunately, isopropanol is giving a very high back pressure. So depending on the pump you have available, you can go to a flow rate of 0.2, 0.3 milliliters only, because then you are already higher than 200 bars. As I said, the columns can withstand 400 bars. So you can go as high as you want, as long as you are staying below 400 bars. And then the volume of the column is 600 microliters, more or less. So inside the column, we know that from the void time of the column. So typically, that's recommendations from column producers is that you take at least 10 column volumes, at least. Which means 6 milliliters.
Yes.
What if the LC columns are contaminated or damaged by aqueous waters?
Normally, when you are not have salt inside, when it's only water, you can flush it with isopropanol, and then again DCM hexane. As long as you do not have injected salts, because when it is a salty solution, it's quite complicated to get these out again, because salts typically have metal ions in it. The metal ions, of course, will absorb on the silica. When you want to get them out, depends on the metal ion. When it is, let's say, it is calcium or magnesium or iron, Unfortunately, you would need to use some ETA solution for that. So it gets really complicated when it is a salty solution. But if it is pure water, just isopropanol, DCM, hexane. So it's about 10 column volumes at least you need for the isopropanol. Unfortunately, it's much more on the final hexane, because removing 100% isopropanol again from the column takes very long time. I think you need at least 50 column volumes, could be even more. Because it is isopropanol by itself, as you know, is an alcohol, and silica particle has OH hydroxide group. So you have perfect retention of isopropanol on it, and to get it out again 100% is a long-term time. So you need a lot of solvent to force everything out of the column. Therefore, first DCM, and then finally hexane. And you can check it by injecting that internal standard without transferring it into GC. As long as you do not have stable retention times for the perylene, the column is not yet on 100% hexane.
What do you mean by stable retention?
When you are having such a column, you will see that perylene will be emitted at 4 minutes. Then it will go further and further. And only when you are in a stable retention time after multiple injections, then you know that the column is finally equilibrated.
Just a quick question. When you talk about hexane, I think in this room they want to ask, is it using the super soft N hexane or any hexane?
In this case, you can use any hexane. In this case, you can use any hexane because it's only for the equilibration of the column. When it's then done, of course, you need to flush through the super salt one. But for the, let's say, for the reactivation and re-equilibration of the column, it's not important which type of hexane you are using.
Sure.
You could also use, if it's better for you, you could also use cyclohexane or N-heptane. That's not important. It's only important to get a non-polar solvent completely flushed inside the column.
About that, based on my understanding, hexane is actually banned in EU for usage.
True. It is used. It is banned when it comes to industry use.
So
it is of course still used in refinery of oil, but you have an exception for N-hexane when it comes to laboratory use.
Okay.
Yeah, but you are right. N-hexane will be banned in the EU, which is also a big topic for the edible oil producers, because one step in the refining of edible oil is an extraction with hexane to get all the oil out of the seeds. And this in future maybe needs to be done with another solvent. But at the moment, everything is done on technical hexane. It's not N-hexane that would be too expensive.
So it won't affect any of the analytical methods, even you foresee the future.
No. Because there is a clear exception for laboratory use. Of course, we have customers not much concerned about N-hexane, but it's more the dichloromethane that they are concerned about. And let me answer it that way. When I would have more time in the lab, I have ideas to switch also hexane and dichloromethane to another solvent. But yeah, I have a lot of stuff to do.
So you guys are actually thinking of switching it, so just to foresee the changes.
First, because it's more pressing on the dichloromethane side, but yeah, we have also at least on the list, but with very low priority when it comes to the N-hexane, because it is easy. You could use just cyclohexane, or even the use of isohexane would be fine. But again, when it comes to the purity, which is a big issue, because as you already know from N-hexane, it's sometimes really problematic to get pure N-hexane. It can be more problematic when we are taking other solvents.
I think everyone's a bit oversaturated.
Yeah.
Shall we go for our lunch break?
Yeah.
Thank you so much. If nobody even dares to use the washroom, we are teaching. So yes, this is also an opportunity for us.
Please interrupt me whenever you want. Also, when you need a break. Typically, I have to admit, this presentation typically is faster finished. Yeah, but we have a lot of questions in between. Perfectly fine. So
Okay, thank you so much.
column, you cannot use it anymore, obviously. So this is a big issue but normally only possible when you do very big mistakes. So, for instance, completely wrong penetration depth, but not only for a few millimeters, but highly wrong. Despite that, as I said, salts are a problem. So as soon as you're injecting salts, which is unfortunately the case with our, you might know, when we are quenching the reaction solution after epoxidation, we are using sodium metabisulfate. And that unfortunately obviously has sodium cations inside. So could be a problem when you're injecting too much of that. The good thing is sodium ions typically can be flushed out of a column when you're flushing it on just water. So you can try flushing a column on isopropanol, then you're going to water, and then you're going back to isopropanol, dichloromethane, hexane. So then typically mono cations should be flushable out of such a column. It gets complicated when you have multiple charged cations. Then it's what I've said about EDTA flushing and all stuff, which is much too complicated. Of course, first of all, you should not even get into this situation. Therefore, you might have noticed, and when we look in front of the instrument, we will see it. We also have an HPLC pre-column. So typically, this is where the junk should be stick in the first place. What I have observed is many people just do not exchange the pre-column because we typically do not have much problems with higher back pressures. I know from my experiences, people tend to exchange pre-columns only when they are seeing back pressure issues or something, and they are just trying to, maybe it's coming from the pre-column. But as long as the chromatography looks okay, people do not change pre-columns. That is for MOAH instrument. I would really comment, will be later, that changing the pre-column should be done on a regular basis, because whenever you have traces of salts or whatever, it will be first absorbed on the pre-column, which is much cheaper to exchange than the whole HPLC column. Okay. So now that we know how our instrument works in theory, I want to show you just a practical example. So this is just a palm oil, not important which one. And it was also treated by epoxidation, of course. It's not important for now to understand that. But in the end, what we are getting is 2 chromatograms, when aligned, have a hump very comparable in shape. Yeah, so that's what I've meant before in the morning when I was talking about looking into the shape of the chromatograms. Typically, I know that's nice palm fat, but typically that's what you should expect for a nice mineral oil hump. I know absolutely there are combinations of humps and what I've explained before with missing parts in the front, missing parts in the end, etc. But from a theoretical point of view, where we start right now, it should look like that. And since both columns, so these are 2 different GC columns we are using that are not connected to each other, typically it can be possible that you have a shift between both channels. That's one of the things we are checking doing FAT, SAT. Also, when the customer uses an instrument, it's a check that is easily done and can be corrected also in a quite easy way. So that's now the first practical stuff we are doing, and I need to ask Elton. I've sent you Gravex mineral oil samples.
Yes, correct.
We need that right now. because what we will do as a very, very first thing, we will not talk about food stuff in the beginning. What I want you to do is what we have seen in the chromatograms up to now, analyzing mineral oil, just in solvent. Yeah, so what we will do is Shell Gravex 913, that's a very easy base oil. So it's called base oil because it's the base for other products. So for instance, when you're taking paint for the walls, and it's not water-based, when it's oil-based, that would be such a base oil as a carrier for such paint. And thank you. And what we will do, so I have here a vial where there's pure Gravex inside. So it's a clear liquid. So it doesn't have any color, highly refined, but it has known amount of MOSH and MOAH. And what we will do now in the beginning is, what I want you to do, and you could do it all by yourself, or you do it in groups, because we only have one instrument. It doesn't make sense to inject 20 times the same. But what we will do is, we will take 10 to 20 milligrams, which is just, in fact, when you take a glass pipette, it's only one drop, that's essentially 10 to 20 milligrams. We'll put this into a 20 ml headspace vial. So these are the ones we are also typically using on the instrument. You need the exact weight, so I hope we have a good balance somewhere here.
Yes.
But it's fantastic. I think you are producing very nice balances, so I think you will have one. It is sufficient to put as exact as possible 10 milliliter of hexane inside. Typically, when we want to do it very precise, we need to use a volumetric flask to get exactly with the meniscus inside there, 10 milliliter, but for our experiments, it's fine. So 10 milliliter of N-hexane. From that solution, after mixing, we are transferring 1 milliliter into a small HPLC vial. And we are adding additionally 10 microliter of the stock solution of our internal standard. Up to there, any questions? What we then do is make sure that the instrument is ready to be used. I just prepared that oil ready for you, but we will inject 10 microliters of that into the instrument. And we will see how the chromatography looks like. And of course, you will also do the quantitation by yourself in the most easiest way, which means in Excel. Okay?
In Excel.
Yeah.
Just a clarification, if we normally for such spiking how many milligram in terms of accuracy there's no to record down?
For our experiments here, it's sufficient when you have 10 to 20 milligram, when you have, I would say, 1 or 2 digits. So that's typically, so in our facility, we have a 4 digits balance, which is not very precise, so to say, but it would then be 20 points whatever milligrams. That's fine for our accuracy we need right here. In real life experiments, you would typically, when we talk about sample quantity, we are talking about grams. So it's not in the milligram range. But for here, since we do not have a sample matrix and do our spiking from the stock Gravex or from the pure Gravex in an undiluted way, the more digits you have, the better. The instrument looks like that for the ones who have not seen it at the moment. I see that it works on the wall, but not on screen. Okay. We only need this tray. Yeah. So we are filling our solution into a small HPLC vial, put it somewhere in the rack. You just need to know the location. And after that, I already put all the information you need for that into here. That's basically the Kronos line you need in your injection. That's our Kronos method. A comment what we are doing. So in fact, it's 1 milliliter of Gravex. That were obviously my numbers. That will not be your numbers. Yeah. So our concentration, the amount of internal standard, the position injection volume, give it a nice name, and then just click on create schedule and start, and then everything else is done by the instrument. Okay? That's for now. So now we need to find a balance and somebody who's capable of using it.
Split into groups.
How many sample only one?
And for this stage, we just need one sample.
Tomorrow.
Sample the most challenging one
We do together.
Yeah. But somebody has to be the weighing. Somebody has to do the weighing.
Yes.
So let's move to the lab.
You should have now a chromatogram that pretty much looks like these two. So that's where the ones I measured quite some time ago. So now it comes to how do we quantify it, or how you will quantify it. So I will not tell you how to use lab solution. I think you are the experts in that. What you now need to accomplish is in teams, or if you want to do it manually, however, what you need to get for quantitation is you need to draw a line below the two humps. So you need to get the area of the total hump. What you also need to accomplish is on the S you like for now, as we have learned, these compounds here are not part of the mineral oil. So it means when you get the total area, you need to cut them or subtract them manually or whatever. So for now, just plain Excel. Yeah. So you take the complete area, you are subtracting these peaks. You can just integrate them in a second approach, whatever. But we need to have the area of the total hump because that's from the mineral oil. I marked for you the peaks used for quantitation. That's on the MOSH fraction, the first one here. And for the MOAH fraction, it's the last one here. Okay, so these are the peak areas you need for the quantitation. And then I put in here the formula for the quantitation. So you need a copy of the chromatogram from the computer. If you have lab solution on your own computer, you can do it here, or you need to do it in front of the instrument if you do not have lab solution. Yeah, you take the chromatogram from that instrument. We just have acquired right now. And we know the amount of internal standard we have added. That was 10 microliter. The weight concentration of the two compounds, they have the same. It's 300 nanogram per microliter. So these are known numbers. Important to know, and I think this one here needs to be adapted when you are working on the 11 milliliter vial. Don't know which one we have injected right now, but think that you only took 1/10 or 1/11 of the solution from the big vial, so you need to update that. That's the amount used of the mineral oil. So when we talk about 15 milligrams, or it was 25 in the one case and 11 in the second one, or whatever, 1/10 or 1/11 of that. Put the numbers in the formula and let me know what you got from that. In milligram per kilogram in the end, which is also the same as nanogram per milligram, but you need to calculate now a little bit.
Yeah. I know the data a while about
Thank you.
how to share teams. Everyone.
Maybe you use the laptop the screen to show the lab solutions.
Take away lah. You cannot send to the team floor.
Yeah.
Like get a screenshot.
Now is your time to practice.
What do you want to send? Only the files like this.
Unless you share the file.
Wait, all the time. And all of the I don't have left. You tell me that solution is no point. Then the team.
It's not yet too bad.
Okay, in no case, you sit down or try.
You try. I try to order.
Because if you integrate that in
Itu adalah sebuah
internal standard is
dan lagi satu bit satu lepas bit dan satu belajar sintetis
just click this.
satu dapat 9 satu 2 kos.
Jadi dah.
Kira kan saya untuk cuahan tolak nombor itu we get the dapat area of the tapi kita tak kira yang lain dia
So that's minus.
So I said,
Or you do better than the
area adalah
Yes.
grading baca dan LSI B and so B adalah C13 area adalah area saja
Yes, I need to minus
You change from the 5 more, right?
Yeah.
It's the 28.
And was it this
If you have all book, that's what it's fine. Yeah, I think that's the 9 is still acquired. I don't think that it is already ready.
Where's the
Is that the 110?
I guess so. The one you have in new, the one is 110 or
this one is
I said the photo.
360, 363.
The wire.
3603663.
So this one is 181.
น้ำหนักเท่ากันเชื่อ
Second pin, no?
this is in annual.
Okay, then. So minus
Then that's all right. Yeah. Then do for MOAH. Manual integration. Clear. So this one I need to start from here. Or so technically you can start around that time. Making a start.
ทำให้ตัดไม่ได้มีไม่แก่เรียนเราไม่ได้ทำอะไรมาแค่คิด
This one actually is
ที่เหลือเหมือนเดิมมันก็เป็นพวกนี้น้ำหนักทุกอย่าง
so I should use this one.
Bring to pick up.
That's at 10 milligram.
Oh, this is on 11, sorry. So, need to because this is 11.
I think the number is already the concentration, right? Or what you are going to promise?
No, this is
Match the way.
Divided by 11, I think it will be the 1007.
กับตัวเลขที่เขาช่างมาเขาหาที่มันละลายออกได้เลยแต่แค่สวยนี่คือวิจัยอะไรหน้าที่เราที่เขาที่เราวิจัยทำไมเรียนมาคิดเข้าถูกแล้วมันก็ออกมาเป็นพีพีเลยพีพีแล้ว
Okay. That's good.
เขาคิดเองได้
เรื่องเรื่องแล้ว
ไอ้ที่มัน
ขึ้นหรือขึ้น
include validity using the mobile.
So, yeah, that's
Yeah, will be 5
so this
00088. Okay.
But then this is an 8.
yeah, this is 8.
Yeah.
The one is this.
Yeah, 1045. Nice. 1054.
And this is the first pin.
First pick.
377.
Two, eight,
And this one actually
yeah. First pick is what?
189.
189.
Then minus this.
ชื่อของหลอก
ตัว
แค่ตัวนะ
This
มันต้อง
11 5 8
023.
023.
So I do it so but for the next integration is that from 9.5 to 9.5 so what you said is basically to 9.5 to 11.
Oh, so that's MOSH. This one MOSH.
เป็นมอด
มีการเกิดปวดแรก
ขวดที่ท่านที่เป็นกันเลย
which way for the
That's it. Did it minus up?
subtract
It automatically subtract. You see how many is more big. Automatically subtract. You try. So it's not. They have to one software. You let solution, you let overlap.
Yours is not like that.
You let solution.
The number is okay.
Yeah, so okay. If like that, then you just take this one for MOAH. So this one for MOSH. 103. Yeah.
For one.
And now you need to have the same information also for MOAH.
103.
10376.
The FID, same calculation just with the with the proper number.
Right? So this one, the MOAH is 4124790.
okay
So this one is 1.0 plus the calculation.
Can you open MOSH again? MOSH again.
MOSH again. Yeah, MOSH again. This one. 376. Okay. Yeah. So now we have second time.
Oh.
then you have to indicate the internal standard area right
I need to indicate.
Again, on top, just select FID2, then it's the same, so completely independent.
10
Oh.
T is
C.
yes you must why
So
T is 10 3 6
307 to
3 7 7 2 and 9
and then the
so the 8 something is a C11.
yeah C11 is RT10 3 that's the definition.
Second one. 7.36 or the solution.
You can just copy that number into Excel and you do not need to, that's true. You don't need to write it.
C13 is 189.
Yeah.
But why I don't have this one? I can then find this C. Okay. So I will have it. So see the digit.
17.5.
Oh, so Cho is the last one.
Yes.
So this is the hub.
Yeah.
MOSH.
Oh, MOSH.
MOSH. UNP, right? Okay. So this should be more. Okay. Then I should
The question is,
So this is our results.
yes.
Yeah.
Random area. Okay. Correct.
Okay.
So this is MOSH. So this is MOAH. What the hell?
Yeah. Element
You don't need internet. The first one you need.
the first one.
The first one.
5B.
TVB。哦，我这个什么讲的吧？现在我只是要
Then the last one. The last one.
TV 啊，哪个选？要
Okay, so now reading all these, right?
Oh.
All together. Oh, okay. So first one is side B. Which is then one then TVB,
Yeah, the man.
Then last one.
So this is more.
Yeah.
219.
Alright.
So correct.
Alright.
Okay.
Good. Come.
Okay. So we have
Great. I need this one. Yes.
yeah.
All this bracket is the
ไอเรียน
The second one.
ไม่เจ็ดไม่เจ็ด
ไม่ถึงเท่าไหร่
เสร็จแล้วพี่เอาอะไรนะ
มันไม่ของมันไม่เข้าเลยนะแต่ลองมาเจ็ดไม่มันได้ไอเดียเท่าไหร่ไม่ดู
อันไหนอ่ะ
ออกมาเชื่อมองแล้วดิก้า
This is
ยี่สิบเก้ามันไม่ได้ทำติด
อ้าวเขาทำเป็นดิชั่นเลย มีโปสเตอร์
ไม่ใช่หน้าไหม
yeah.
1.087.
It's MOAH 760 790 is
Around, so what you like first of all?
ที่เป็น
เดี๋ยวก็ไปเขียนใหม่
จะไม่มีก็ไป
So do we all get a few numbers? Yeah. So maybe we start with MOSH. Has somebody numbers for me?
MOSH 1.3.
The how?
Final calculation, so final result.
You mean, sorry?
The final result. In
The how actually?
794,000. 794,000.
94,000.
Oh, I didn't know those real right?
Just write it that way, yeah. What was your result?
770,315.
Yeah, I just need in 100,000, so 770,000. The same unit. Anybody else with the final result? While you're still calculating. Okay, take your time. And for the ones not calculating, anymore. You can think about what does that mean, and does it make sense what we are seeing here? Because of course that's a quite high number, as you know. We talked about 2 milligram per kilogram before. I will go to the restroom, and when I'm back, maybe you have an answer.
Anh điคิดค่าพื้นที่มันก่อน เล็กดีเป็นของเจ็ดหก
那么说，在个人化这消费者。
ERAB หลักแสนถ้าไม่เป็น8 ช่องไม่เป็น59ติดแต่5ติด59
ทำไมมันตัดกันหมดแล้วมันเหลือนาโนกรัมเปอร์มิลลิกรัมใช่ไหมล่ะ
Suppose value
มิลลิกรัมนาโนไมโครกรัมเปอร์กรัมมิลลิกรัมเปอร์กิโลกรัมไม่ใช่อะไรมิลลิกรัมวะ มันอยู่อินดิเคตแล้วมีสูงไม่สูงสูงเลยไหม
Probably just pick one.
Yeah, that's why I
Yeah, that's one more observation, of course. Also pointing out how complicated or why it is understandable why there's also high deviation between different labs, because it highly depends also on integration. But to be honest, these two numbers look very much the same. Yeah? So it's not
really acceptable.
We'll talk about that if it is acceptable or not, but first of all, we need to find out if everybody else gets a similar number.
You got how much? You got high? No, I get small. You reach why is so small? Why small?
I think only.
Why small? Yeah.
Soลองให้ฟังกว่าอ๋อนั่นหมอมอสเพราะว่าจะไปเล่นเขาโอเคไม่เก็บผ้าเก็บผ้าที่มีเป็นจากมันไหนเดียวกันมันจะคนอันนี้ติดเสกว่าจะเป็นเบอร์ทั้งหมดอะไรครับต้องวิ่งได้แบบเปลี่ยนแปลงใช่ไหมหน้าไปแล้วอันนี้เป็นอะไร
What was your more number?
But the one that the wrong one to be back. The weight of the mineral,
Okay, so this is common facts. The other one is then you was divided by
And then I really hate it.
ไม่ใช่บางที่แปลกในอันนั้นขวดที่9อีกตัวนั้นขวดที่9มันหนักกว่าขวดที่9
Then the V is the volume, and the area of I is this one. And then the small one is
1.2.
oh,
depends on
so 1.0 area is of is what?
ตัวคิดแล้วผมไม่ได้สงสัยว่าที่ไป น่าจะมี2แบบเพศในเซมเพน
What's the way?
Why is only 75?
ปล่อยดีคนนั้นอยู่
divide 1000. So I didn't divide 1000. Oh, okay.
No.
So
มอง
this is what
The more about the 283.
Well, 我觉得有点跟那三个人的I think 大家都差不多的。The rest same right? 都 same right?
ก็ถูกไม่ได้ตกง่าย
So it's
265.3. 265.
oh, it's too low then.
We don't know the real true value.
The other one is my value.
ไม่ได้26เลยที่บิด
We of standard.
ตัวเลขเท่ากับตัวเลขเท่ากับอ๋อเขาจะเป็น103
Oh my god.
Is you need to the number something.
Even if you can't integrate, that's a problem. 你拉多少都会影响。
Right. Then the other one is
You still drink so.
安奇白两。
So,
好了，我他背做掉。
其他的那个4.5%是说到
the below is the second sample.
The second one.
Yeah, the 2.4 actually.
ทำไมไม่ต้องการ
我在那里除以前，
จริงๆมันควรจะเท่ากันดีกว่าเพราะฉะนั้นเป็นอย่างนี้แบบไม่ใช่
这是礼拜1到的。
ก็ไม่เยอะ
礼拜1到2个月。
ติดทั้งสแตนดาร์ดไป
哎，我来怎么搞？应该是红了。
那个
我搞了一个。
ที่มันต้องสแตนดาร์ดเอาไหนที่เป็นแจ้งอีกแล้ว
我讲大概现在
ของเขาทำไมมันไม่ถูกกันเขาไป
你们中国的100，那你们的100不知道。
我在the first three number only. Marketing only.
The problem is in Germany, to separate it by a dot, but I just realized that it's a comma.
All the chemistry gone already.
哦，这样是他的意思是这样啦，他的意思是这样，
还有黄了，肯定。
他的意思是这样啊。
แต่มันอยู่ที่คนในเขต
对，这个是我不是他的意思。
They just collected now our 3 results from the same sample. So we can skip the second one because hopefully it will be the same result. But maybe we can just proceed from the three pairs of number we are having here. First of all, has anybody an idea who made these numbers some sense, or is it total nonsense? What do we see here?
Too high.
I just at the moment, please ignore that we have different numbers for the same sample. Yeah, so of course that's because you all did some stuff differently. It's first of all the dimension of the number. It's 794,000 nanogram per milligram, which is, I already wrote it that on the slide. It's the same as milligram per kilogram. That's the same unit. So I will just write it in milligram per kilogram. But from the dimension, does it make sense what we have here, or have you expected some other results? Do you have any idea what you are seeing there? First of all, maybe we are going one step back. Do you understand what you have done here from the calculation point of view?
Minus all the writing things, you just want to know.
Just as if everybody has understood the formula itself, so why are these numbers in the way we are using them? Is that clear to everybody, or should I just quickly explain what we are doing here?
Yes.
Okay. MOSH, since we are not doing calibration, as you have just noticed by now, there were no calibration curve, nothing. MOSH is just based on simple calculation of an internal standard in relation to our hump. So that's what we are doing here. We have an internal standard for each chromatogram. We have a hump in each chromatogram. And what we are doing is we are taking the ratio of our areas. And as we know the amount of internal standard added, that's in fact this factor here. We know the concentration, we know the volume, and we are multiplying that with the ratio of our hump divided by internal standard. Then this is giving us the amount of hump on column in the system, or in fact not in the system, in relation to the concentration of the internal standard. Yeah, we know that we have injected, or we have put into the vial 3,000 nanograms of internal standard. When we multiply that by this ratio, we know that our hump has then an amount of, I don't know, 5,000 nanograms. This needs to be divided by the sample amount because we want to know the percentage or the proportion of our mineral oil, or MOSH or MOAH, in in regard of our sample. So this is finally divided by the amount of the sample. In this case, our sample was mineral oil. This is why this formula looks like that. And in the end, it's already in the final unit milligram per kilogram. So that's the unit, or that's the formula used for all type of quantitation. The sample amount is, of course, not always mineral oil. It's in fact then our food content. It's only here for the very first example that we talk about mineral oil as a sample. And when we are analyzing mineral oil, we have now analyzed pure mineral oil. What do you expect is the main component in mineral oil? It is mineral oil. So we are expecting 100% mineral oil.
Yes.
And just to let you know, 10,000 milligram per kilogram is the same as 1%. So in fact, what we are seeing here is 31% MOAH and around 75 to 79% MOSH. Yeah, and this sample, when you would have done it multiple times and multiple users, blah 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 blah, then the amount of MOAH in that sample is 26%, which is exactly one of the results we are having here, and it should be in the range of 73% MOSH. Yeah, so not too bad, but also not too good in regard of that it was only one chromatogram that was interpreted by all of you, at least in three groups separately. But it also shows one of the biggest problems in MOSH MOAH, that it is highly dependent on interpretation of the people integrating the chromatograms. Yeah. So that's one of the basic problems, because there is no, so sometimes at least, this is in fact a very easy one, but how to draw the baseline under the hum, or where to start or where to end, is not always clearly defined. I've seen, and this is also one of the, I think, default behaviors of lab solution, that lab solution tends to put not a straight line under hum, but something like that. Yeah, and of course, then you get higher peak or hum areas compared to a straight line. But the numbers are exactly as expected. You see that there seems to be a slight problem when it comes to the amount of internal standard or amount of hexane we have added. The sum of all of them is higher than 100%.
Yeah.
Yes.
Does it make sense?
Obviously not. It is the case because the amount of internal standards probably is not exactly the one as we are expecting it. We think we have added 10 microliters, but when you do that manually in a 100 microliter syringe, that was one reason why I asked, why are you using a 100 microliter syringe? It is much more precise when you would use a 10 microliter syringe, because on the scale, it's very hard to see if it is 10 microliter, 9 microliter, or 11 microliter, which is then again giving already some kind of deviation. But for very first run with multiple people involved, not too bad. Okay?
Guys, I still haven't forget my experience.
No, but the numbers make perfectly sense from the dimension. Please ignore for now that it's more than 100%, because that's most likely that it was not 10 microliter, because it's easy to add 9 or 11 into it, or even 12 or 8. Yeah. Okay, does it make sense for everybody? Depending on how long you still want to work today, I don't know. Have you plans when you want to stop?
Not really on the tree.
Huh?
Yeah, the UV
Yes.
slide.
No.
Usually for the deal. Of the deal.
Then it should be still plenty of time, because now we are doing. Even that is fine, because now you know how to do it.
Yes.
We will now do exactly the same, but for sunflower oil.
Oh, okay.
Yeah, so we will not inject pure mineral oil or diluted mineral oil. We will spike a sunflower oil. We'll spike a sunflower oil with with Gravex and try to quantify if we get the correct result of our spiking. Yeah, I just put it in here. It's not very different to the thing we have done before. What we will do right now is we take an HPLC vial, so a small amber vial. We will put on the balance 300 milligram into the vial. So we need the weight again. We are adding 670 microliter of N-hexane, can be done with the 1 milliliter pipette with a glass extender. Again, 10 microliter internal standard, as precisely as we can. And we are taking 20 microliters of our diluted Gravex solution. So since we now analyzed the first one, I hope we still have the 20 milliliter vial of that, because this is now our spiking solution. We are not spiking with pure mineral oil because that would be too high. We want to create some sunflower oil spiking in a reasonable range, not at 10,000 milligram per kilogram. Because as we already have learned, 1 drop of pure mineral oil is giving you very, very high numbers. So only, again, to understand that 2 milligram per kilogram, we are not talking about liters of mineral oil coming into food. It is just a diluted mineral oil and very small amount. So we are not talking about high contaminations here. It's really just very low contaminations that we are analyzing. Yeah, so that is what we need to do right now. Again, here's the formula for the spiking and the final result. And we are not injecting 10 microliters, but we will inject 67 microliters. I will explain why it is 67 and why it's this odd number. But for now, we more or less do the same as before, but only on sunflower oil. Feel free. Yeah.
Why we use the sunflower oil?
Because sunflower oil, it's not a 100% solution. There will be always cases where, to the best of the knowledge today, GC times GC also does not work. Because you have overlapping areas in the chromatogram where you just cannot separate biogenic interferences from potential mineral oil ones. So this is highly dependent on the use case first. And what I always try to tell customers is many of them already have a GCMS somewhere for pesticides, for MCPD, for whatever. Maybe first try with collect and collect, because you should use that anyhow when you think about GC times GC. Collect a sample and just inject it into a GCMS and just have a look into the chromatogram, because there's essentially no expense there. Yeah, you have the instrument anyway. You're doing a full scan, just have a look into the data. Maybe you get some insights that you did not get by LCGCFI.
Do you have any recommendations? Let's say I do brand collect to collect the MOAH fractions and then to go into a 1B GCMS.
Not more than we have just discussed. So you are collecting the MOAH, you are doing a blowdown, and you want to have a little bit more sensitivity. Then you're doing a full scan over the complete mass range. So at least up to 700 Dalton. Then of course, it's always good to have the list database installed, because there's not a very high chance, but at least you get an impression, or you get also correlation between the mass spectra, and at least you get hits of structures that are maybe related to the one you are looking for. Again, as GC taught us, it's only for identification or conformity, it's not for quantification.
Then you ask that. GC product question. You MMI. Oh, for me.
You like it?
Can I just ask for okay and share us the method for what you need from GCMS?
I can, but don't be surprised. It's the simplest method you can imagine. So there's no magic inside.
Yeah, he asked. It's not no magic.
No, I can send it to you. It is a bunch. Believe me, it is very, very difficult. It's very similar. Yeah.
Thank you so much. We'll try it outside. Thank you.
So
Yeah. We have again graphics inside. You can see that quite clearly. You still need to wait for the final data saving so that you can have a look. I can already show you. Yes.
Okay. So
it's a very similar and all the same. Yeah. So many you will also have the
so we decided to
yeah, so overlap maybe special. I don't know how they do the formula but that's why I'm curious on things like that or whether you're able to separate.
You're picking on one point and then that point actually is your
Yeah, yeah. But then you go with GC like GC, but you can separate like the still not on all the metrics. Some metrics will you do so much, it's only competition with the computer. It's still taking back to that like this matches.
right.
So about GC times GC, it is really up to the customer because it costs at minimum 100,000 euro more. So 150,000 Singapore dollars, more or less, more at least. Depends on what kind of instrument you want to have. And yeah, when it cannot answer 100% of your questions, it's debatable if you want to spend this money. Yeah, for contract lab, it's another story because it's not important if they cannot analyze one or two samples. It's just then for a customer, they are telling the customers, okay, I cannot analyze the sample. We will raise the LOQ, means they are giving just a number that they can quantify till 4 or 5 milligram per kilogram. We cannot tell you if your sample is contaminated with less than this, because this is our raised LOQ. But for a process lab, honestly, for a process lab especially, these solutions are just complex. We have so much experience with process labs when it comes only to the LCG CFRD solution. And even this is, you need highly skilled personnel. And even that is sometimes too complex for them. And as I just pointed out yesterday evening, when we're talking about GC times GC, the times GC means we need to install more columns in the GC oven. And we already now have 4 columns in the GC oven. Depending on the vendor, you have a second oven inside the GC, which makes it very hard for column maintenance, especially since we still need to go to very high oven temperatures. There is a high chance of breakage of the columns. Since we need to use at least at a few points pure silica, you just cannot use everywhere stainless steel. It means in the end, with the high amount of samples and always 370 degrees, then cooling down, heating up, cooling down, heating up, as you know by yourself, the columns will just get brittle and they will just break quite fast. We have one contract lab in Germany with the GCG CFI solution. I think they need to reinstall the column, I don't know, every second week, maybe every 3 weeks, more or less like that.
Oh, you see that?
Because it is always on the connector, because of course the GC often doing the cooling down especially moves a lot, and you have movement on the connectors, and even with the low thermal micro union connectors, even those have enough mass that the column will just break on that by the movement of the column.
Customer didn't calculate that every week, so they change the column, or you just accept. You just accept.
Yeah, that at least for this contract lab, so it's in Kirchhoff, so the most well-known lab for MOSH MOAH all over the world. They know what they are doing and they are adjusted to it. But you can imagine when you have a process lab, that's another story. Especially, there's still no software available for DC touch DC FID evaluation that is as easy as Colibri, for instance, what we will see data illustrating. So GC FID quantitation is still based on Excel. Yeah, so you need to copy numbers into Excel, you need to have an Excel sheet, and you need to do quantitation basically manually. Yeah, so this is important to understand for customers that it's not a turnkey solution. So it's not just click on one button and you will get results for all kinds of samples. It doesn't mean if you have a customer and you want to sell it, perfectly fine, but they need to be aware that this is even more complex than LCGC FID. Therefore, always the recommendation when somebody wants to do GCGC MS or GCGC FID, try to have a distinct instrument with an MMI, for instance, as injector, and use the track and collect on the LCGC FID. Because crazy people always want to have everything combined in one instrument. Not the best idea.
Yeah, crazy and then not talented to use.
This is another story. But I think already by now we can tell that your chromatogram more or less looks like that one.
Yes.
Here you can zoom a little bit into it. That is more or less exactly the same. Yeah. So what we are seeing again, you should know by now that these humps for MOSH and MOAH are coming from the Gravex we have spiked into the sample. Everything else you can see, despite our internal standards, of course, is biogenic olefins or biogenic N-alkanes. Yeah, as I have said before, sunflower oil contains quite a few N-alkanes, not at a very high concentration, at least not for only 300 milligrams, which we have weighted in. But we also have quite a few biogenic olefins. Even here, not too much, but I think you can just zoom quickly into this area. So can you zoom just into this area? Then can you just click on plus a little bit more, just to give a note. Okay. So we have the hump here and the second for MOAH. But when you think about it without knowing what we have done, we have maybe a second hump also here for MOSH. And maybe could it be also somewhere here for MOAH? We cannot tell. First of all, because we only had put 300 milligrams into the vial and we only injected 67 microliters. So this is effectively what we have done is the method for MOSH MOAH analysis that was published in 2016. That is the EN 16995. That was the method that was published back there with an LOQ maximum of 10 milligram per kilogram. Yeah. So we cannot tell, especially in this area here, if there is maybe MOSH or MOAH below, especially those things here. Of course, this is a very big hump. I don't know if anybody of you already has calculated the spiking that we have done. We have a number for that. What was the spiking that we have done for the sample? So what we have spiked into the sample, because we have known concentration of Gravex, it's easily just put it into Excel and give me some number.
government and real applications.
Yeah, for that one here, we do not even need the chromatogram. So this one here is just to calculate what we have spiked into our oil. So this is basically just using the amount on the balance and our results from our Gravex injection before. Honestly, I do not even know. So we need to check that. I think it should be more than 6 ppm. I think it should be in the range of 60 ppm. Have you told me the MOSH or the MOAH result? MOSH? I think it should be 60, around 60.
How many we spike?
20 microliters here. It's on the.
Oh, okay. Sorry.
Yeah.
Concentration was 1 point.
8.7.
Oh, 7.
The MOSH percentage just the same. 70.
Oh.
But you could even use your own result if you are confident with that.
Then and
Yeah, what was the weight of the sample?
the weight of the It's 7.3. Next year, divide numbers, then divide other numbers. Then what we need is spike result. Equal to
Don't forget divide by 100. I think like a percentage. I don't know. We need to find out. I think you need to put in 0.73.
Oh, okay. So I need to divide by 100.
Yeah.
ซึ่งจริงน้ำหนักคือ280
Yeah, this is
วิธีการไม่ใช่ตัวตามตัวกัน
5. Can you show me the formula once again? Yeah. Yeah, it should be around
55 ppm.
And for MOAH, obviously 1/3 maybe of that, more or less. For MOAH, it's obviously the same calculation, only the percentages, another one. Yeah. So that is the expected amount we have put into our sample.
Okay.
Then, of course, the second formula here is for the quantitation. It's basically the same you have used before for the Gravex chromatograph. Then you get a number out of it, and then you compare it to the spiking. The ratio divided by that is called the recovery.
Oh, okay.
Yeah. This is basically the stuff everybody needs to do during method validation. So spiking is part of a typical method validation. So you're taking a mineral oil of known source. This is typically nowadays not Gravex anymore, but it is SN500. SN500 is a certified mineral oil you can buy with a certificate with a known composition of MOSH and MOAH. The only one on the market where you get a certificate. When you take other mineral oils, which is perfectly fine, but you need to manually find out the proportion of MOSH and MOAH.
But usually SN500, what is the percentage? It depends.
SN500 has 32%, but we can look into the certificate if you want it. It's sold by the company also providing ring trial materials. It's called Proof minus ACS. It's a very well-known company selling worldwide when it comes to ring trials for MOSH MOAH.
Yes. 不是不 dash 不是哎不 yes
แล้วเราได้อยู่ตัวเองเราไม่มีเอาแบบที่เลยI don't think it was your journal.
In the method, you will, yes. All I mean, how this scheduled after. This is kind of when you write the schedule is for and normally the scheduled after property is left empty. There's no value inside. When you give a task a property of -1, it means it will be scheduled or it will be executed right after this one before. Okay. When you would give the this one property it would be executed not after that one, but after this one. So it will be shifted to here and will be executed at the same time as this one. And when you have a method where you give all tasks a property of 0, it just means it will be translated. 0 means executed at the beginning of the method, which means it will be translated into this one. So all of our tasks will start at the beginning of the method. Yes, so you can, by that you can program either by relative numbers or something like times whatever. We will transfer and look at what we have to look at when I want to have this way parallel to this one, I need to give the value of either minus 2 or minus 3 transfer. Which means it will be right after but yeah, partially execution
you don't do anything with
number of transfers when you blink it will be also because of minus not the last transfer but the one before.
Which oil can
Yeah, exactly. But we can make a look at in a real method and it's easier to explain. There are parallel methods, not one task after the other. That's now fixed. That's a little mistake in firmware. When you update firmware, it's starting point 1. Accuracy also on the plus. I think 4.24. So it's quite really. Also 4.16. We can have number 4. You can check it in number 4. Yeah, then you can enroll and the one was only 0.5.
I think that's the other one is I need to reach the transmission because we realize that in a translation, so that's we in the design. What's the same schema? We use the long version of the short version. That should be 900 microliter. But what we have observed is even when you stay below 100 microliter, we have observed when you is shortly blocked, and you are creating a vacuum inside. And when the particle is then either blown away or sucked into your the vacuum will create even further than only 900 microliter. So you cannot prevent to have salts on the valve, but the trick is to have water something intermediate polar on the motor, so that you are flushing regularly salt out. That's a typical observation we have in all MCB systems. And what we have implemented at least for new customers was to use water on the dilutor valve to clean salts out of the valve. This one is nightmare. This. 1,000. Divided observation.
That's the tubing itself has volumes of 1.1 so it should be okay, but what we notice in reality is even 9.5 liter you have salt information in the valve.
step.
Yes, I make sure higher throughput instruments, even if I find practice, we will have eventually formation of salts. So an easier solution is just to put water and one flush the whole initial and
So I still working until this issue and now to this
no, but let us when
because we can use that. That's why we request. I check there's no transfer.
Just ignore.
Okay. Okay. So for the ones that are aware of MOSH-MOAH and heard of that, up to now, we only injected according to EN 16995. And to lower our limit of quantitation, we need to think also about these biogenic compounds in the samples and find ways to remove them. There are two classes, what I already mentioned. It's mainly for MOSH, the N-alkanes, the odd-numbered N-alkanes to be precise. And what I just put here is a comparison. Down there, it's olive oil. How it would look like when you would inject it at maximum concentration. So this is then automated workflow and maximum concentration. So not only 300 milligram in a vial, but 1 gram. And we are injecting not only 20 milligrams. That is, in fact, you might have asked why we have answered, why we have injected 67 microliters. 67 microliters times 300 milligrams in 1 milliliter of solvent corresponds to 20 milligram of oil on the column. That's the maximum our HPLC column can hold on. Otherwise, the triglycerides or the edible oil will be flooded into our MOSH or MOAH fraction. That was the limit in the EN 16995 method, and why we cannot just inject more, also more sample. When we would
The switch, just press any of the button.
which
I'm no idea.
Yeah, it was that one. Okay. When we increase our sample amount, for example, by saponification or bigger HPLC column, not important, then we will not get only a little N-alkanes like in the example for the sunflower oil, but the chromatograms tend to look like that. So a lot of N-alkanes from the plant itself. And as you can see in the black chromatogram, it looks like that there is a bigger hump than it is in reality. Yeah, so after aluminum oxide cleanup, that's a secondary cleanup technique we are using. The hump looks like that, while without it looks much bigger. And this is only because of the high amount of N-alkanes from the olive, or in this case olive oil, because these are in such high concentration that they are overloading the GC column, and it looks like that there is a MOSH hump. Okay, just for the ones interested in why N-alkanes are built by a plant. So for olive, that's a nice example. Other plants are doing the same. The N-alkanes are on top of the fruit, and they are synthesized by the plant for humidity control. You can imagine when a plant is in a rainy situation, you do not want to have all the water inside the fruit. On the other side, when it is a very hot day, the plant does not want to lose all the water. Therefore, there is a layer of wax on top of the fruit, synthesized by the plant. And obviously, when olive oil is pressed, this is all also in the oil. So we need to think about that. That's for the aluminum oxide cleanup, because aluminum oxide is a material which absorbs mainly long chain N-alkanes. So a technique very nicely suited, we will talk about this tomorrow, very nicely suited for removal of those compounds more or less specifically. Again, not 100% specific, but to a very high content. The other thing is olefins, which is a problem in the MOAH fraction, because easiest example is red palm oil. Red palm oil contains a high amount of carotene, beta-carotene. And when you would just inject in the same way as we have before, you get a chromatogram that just looks like that. Yeah, so this hump here is not MOAH, it's beta-carotene. Because beta-carotene, because of the unsaturated nature of it, so the double bonds we are having here, on silica gel, it is not possible for a perfect separation between unsaturated hydrocarbons and aromatic hydrocarbons. They have more or less the same retention on silica gel, and everything with more than one double bond, so you need at least to have 2 double bonds, will be eluted in the MOAH fraction. 1 double bond is still in the MOSH fraction, 2 double bonds is in the MOAH fraction. And therefore, we have something called epoxidation. Epoxidation is a chemical reaction that transforms those compounds with a double bond into epoxides. Yeah, so epoxidation is the reaction to create epoxides. So epoxides is essentially just a double bond in a 3-ring system with an oxygen. This compound then, because of the oxygen, has a much higher retention on the silica gel and is then removed chromatographically on the silica gel. So the idea is we are derivativizing our biogenic compounds into something else, so then we can remove it on the HPLC side. That's the idea behind epoxidation. And that's for now, for today, because I think you have heard a lot for today, because we will do both of it tomorrow morning on the instrument. Okay?